So the tutorial is basically organized by the two Munich universities with the LMU, the Ludwig Maximilian University, and the TUM, the Technical University of Munich. And from the LMU side, our speakers organizers are Björn Ommer, who is heading the machine vision and learning group at LMU, and before that he was leading the computer vision group at Heidelberg. And there has been quite some papers on deep metric learning over the last couple of years from this group. So there's a lot of expertise there, including myself, I'm currently a postdoc there. And from the TUM side, from the Technical University of Munich, there's Jenny Seidenschwarz, who's a PhD student with the dynamic learning group, dynamic vision and learning group at TUM, which is headed by Laura Leal-Teiché, who's also a principal scientist at Argo AI. And there's also Ismail Elezi, who's a postdoc in the group. And Jenny and Ismail together, they published quite some recent state-of-the-art models on DML. So there's also a lot of expertise from that side. So yeah, we got you covered on DML today. And the last thing that I would like to talk in the opening is the schedule. So after the intro, the opening, there will be first a talk by Björn Ommer, introducing us to similarity learning. And after that, there will be two talks covering like the current typical training setup of DML models, including all the important concepts, objective function, and whatever is important to get your model going. And the following two talks are then all about evaluation and best practices. So what you typically should do in order to fairly evaluate your model, and also maybe some outlooks of how to improve the current protocol of evaluation. And the closing talk will then be given by Jenny, who's connecting DML to other fields, because DML, although sometimes this may not be apparent, is actually can be like those concepts and objective functions can be found in a lot of other fields as well. And yeah, to close the tutorial, then we will have time for some general questions and closing remarks. So we will try to find time in between talks to answer all your questions. But if you didn't get a chance to ask a question, you can also wait until after the tutorial, because there we will have, I guess, sufficient time to cover all the remaining and outstanding questions. Okay, and then without further ado, I would like to call Björn to the stage to give his introduction to similarity learning. Yeah, welcome.
Welcome to the tutorial. I'm kind of the opening band for Jenny and Timo and Ismail, who will introduce you then in more detail. But before that, I wanted to give you a bit of the big picture of deep metric learning, visual similarity learning. I will, with you, review some of the key concepts in this field. We will look at where that is all coming from and where it is presently headed. And that is, we will then look at some of the present challenges. Later on in the talk, we will then pick up on several of these details. So since we're here at CVPR, I wanted to start up with the grand goal that we do have, not just in metric learning and machine learning in general, specifically in the field of computer vision. Machine learning itself evidently tries to solve tasks such as classification or regression. The question is that really the grand goal of machine learning computer vision? And I would say that is much too small of an objective. Maybe it's learning a representation of our world, especially of our visual world out there, taking all the imagery in, compiling that into these days into neural network and learning a representation of what's out there. But I guess that is also still too small. So what is missing? What is missing is not so much that we attach just names to individual objects. There are our humble object detection tasks, for instance, and image classification tasks. But what is actually missing are the interactions, the semantic interdependencies of different objects in the scene. I guess that we need to actually really provide meaning to a scene. Relations matter for a lot of applications then down the road in computer vision. Just consider this scenario where you have a lot of data provided, and the first thing that you might ask for is a classification task. And you can do nearest neighbor-based classification, where you ask what this question mark here, what class you would want to attach to this question mark, based on the nearest neighbors. You may want to estimate the density around this point, or going further, even do retrieval based on the nearest neighbors. That's a very easy approach without any further classification. You just take in the data and then ask like what samples may be nearby, and then image retrieval you could implement that way. Next thing might be clustering, grouping challenges where you have a lot of data provided and you need relations to estimate centroids prototypes that are prototypical of what we're looking at here. And then evidently, if you're living in a high dimensional feature space, you would or may want to visualize the representations that you're seeing. And that means you need to project them from a high dimensional space onto the two-dimensional plane that you can see here on the screen to visualize the true underlying structure. Now, all of that eventually does not really work or isn't feasible in the pixel space. All of that only works once we map into a domain that is feasible to process by a computer, and that's not pixels. So we need a mapping onto a representation that facilitates further processing. Further processing in that case might be a classification task. But doing that on the pixels that we started with ain't possible, right? I mean, that only works if you have features that provide you with more semantic information. Other things that you might ask for are regression or grouping tasks, and they also don't work just in the space of individual pixel colors. You may not even just be interested in these processings that map things down to a low dimensional space, but even something which maps it to higher up, such as a segmentation or a visual synthesis. Now, how do we find these features and what is their importance? In his classical book, Berthold Horn wrote that if you have problems with any of these follow-up challenges that I just demonstrated, you should not so much look for more clever tricks to develop a better classifier afterwards or something like that, but what you should actually be looking for are better features there. And that is evidently the challenge that we are all here at this conference and beyond are facing, because the reality comes with a lot of intra-class variability. Just look at this classical problem almost, where you want to find maniculant patches on your screen, on your skin, tumor there, and you want to distinguish that from benign tissue. You have a lot of variability in each of these two classes, and modeling each of these classes individually and modeling what separates one from the other, what makes your skin in that case cancerous, is for that reason a tricky undertaking, because you need a model that embraces all of this interclass variability and models that for good. So, yeah, okay, I hope that's close enough. It's just that I'm probably the wrong scale for this micro here. So, all right. So we need to find better features. That's easier said than done because of the challenges that I just showed. And the first one is we need to become invariant with respect to all of the things that actually don't matter for the task at hand. And the first one being all of these variabilities there due to clutter, whatever that clutter might be. But evidently we need to be careful not throwing out too much, because what is gone, you have a hard time to recover afterwards. And you need to preserve essential characteristics for the task at hand. If you want to separate cats from dogs here, evidently losing features that are critical just so that you take care of the invariance would risk at that case having these characteristics actually being dropped. So we see a trade-off between both of these, and that makes the task so challenging. Typically, we also want these intermediate representations, these features, to have a smaller dimensionality than our input images in that case, for regularization purposes, to better generalize to new scenarios, for efficiency and the like. Now, just as a little bit of an aside, if we have invariances now established in a model, which is a good classifier here, classifies in this object as a wolf, that eventually amounts to having in a latent representation here in orange, these tiny vectors that you see there, corresponding to an equivalence class. A lot of images input to the neural network produce exactly the same feature vector. And on that level of the feature vector, you cannot distinguish them from another anymore. In this recent work, we then built on an invertible neural network that allowed us to project these representations back into the image domain to directly visualize all of this equivalence class, so an approach which eventually enabled you to sample from this class of invariances to reconstruct that and to then figure out what invariances your model has learned at this final layer of representation or in earlier layers. And you can see that the invariances, the later you are in the neural network, evidently are more than in earlier layers. So what characteristics that are here dropped should we actually retain? And which ones can we afford, or should we even want to drop? If I'm provided with here a bunch of images in a high dimensional feature space, I might ask for a classification scenario and then separate these two classes here, in that case, male and female, from another. And when I do that, I get some structure. But is that really all the structure that we care about? I mean, shouldn't we also here on one of these classes have a better sort of representation of the interactions there? You see several pictures of the same person, just from different angles and so on. And shouldn't they be better sorted? And that's exactly what we want, right? We want a richer, potentially a more fine-grained representation. So assume somebody provides you with these positive and negative constraints of things which should be similar and things which should be dissimilar. And then you would want the positive ones, the similar ones, to be closer together and the negative ones to be further away. So essentially you would want to have a representation like that here in a lower dimensional, here portrayed as a two-dimensional representation. And that is precisely what metric learning seeks. Now, there's not just one notion of similarity. There's evidently plenty ways that you could consider objects to be similar, based on their color, as you see here at the top, based on the viewpoint being the same, or based on classes. And the last of these is typically assumed or considered in metric learning applications. Now, back to our setting. We have these constraints. We want to map them into a low dimensional space where similar entities are nearby. And the idea for that is essentially learning a mapping function, here depicted as psi, so that semantic relations in the image domain, semantic relationships between the entities xij that you're starting with, are depicted by metric distances in your embedding base. So essentially we go for a mapping so that here in that case, a Euclidean mapping, a Euclidean metric after the mapping corresponds to semantic distances in the original input space. There are a lot of classical approaches which achieves that, especially in the linear scenario, like PCA, LDA, convex optimization, and so on. Now, what is such a metric that we've just seen? We here assume this D here being, for instance, like a Euclidean metric after doing this embedding. What is this thing? Well, assume that you have an input space, X here. You take a pair of images, for instance, you map them to a non-negative number. And this mapping should fulfill several axioms. First of all, you would want, if you have twice the same point, to evidently get zero distance out there. In that case, you would have a pseudo-metric. If you could also deduce from the distance being zero that it is the same point, the other way around. If the distance is zero, if you could then also infer that you're actually looking at the same point, then you would actually have a full-up metric. You want this thing to be symmetric, and you want the triangular inequality to hold, so sub-additivity. Any detour that you go should only increase the distance. Now, metric learning research can be sort of subdivided into, here it shows 5 different sub areas. And I, in the following, want to go a little bit through this taxonomy then. First of all, it's evidently the amount of supervision that you have provided. If you're looking at a totally unsupervised approach, you're more like in representational learning. But with metric learning, we typically consider the fully supervised scenario, but there are also weakly supervised and semi-supervised approaches. Then the form of the metric actually matters. And on the following slides, I will review like where it started and where we presently are, evidently starting with simple linear mappings and going to more complicated nonlinear mappings. The scalability is an issue. Yeah? Earlier approaches could learn complicated nonlinear functions, but did not scale to large numbers of training samples. And then whether you have a local or global approach and whether you reduce the dimensionality in your mapping. So it kind of all started with Mahalanobis distance learning, in which case you assume that you measure distances in your original space and then scale these distances by means of a matrix, a linear projection. If this matrix is the inverse of the covariance matrix, you're having a Mahalanobis distance. If it's the identity matrix, we have the humble Euclidean metric that we already looked at. If I now take this M and replace it by L transposed L, and then push this L into the first and the second factor, you see that what we started up with, namely measuring distances in the original space and then applying a linear projection, is the same as projecting the data points and then measuring the distance in the target space. And that is what we're going to exploit later on. Typically, this mapping has a rank which is slower than the dimensionality, which means that we are projecting to a low dimensional embedding, which has the benefit of regularizing and better generalizing and so on. But the challenges of these kind of approaches are, and here's a classical NURBS paper mentioned, that you need to assure positive semi-definiteness of this matrix, which typically comes with cubic complexity. That you, in that case, require rank constraints as a regularization to make sure that your mapping is properly regularized, and that actually leads to this task being NP-hard. An alternative to that is just dropping the symmetry constraint, but with that you allow these axioms that I just showed to be violated, so we're technically not having a metric anymore, and with that you would end up with a bilinear form, which you see here depicted. Now, as an aside, when we reason about similarities as human beings, it's also typically not that we have a full up metric, meaning like we contradict ourselves when we are ranking things. And a lot of times it's just that we are typically not aware, or we don't want to be aware of these intermediate contradictions that we're doing in our heads. Now, how can we go beyond linearity? Linearity is nice due to this convexity and the robustness that we have with respect to overfitting. But if we want to go beyond, then we could eventually represent nonlinear functions and nonlinear structure. And the kind of first approach back in the day of kernel methods was evidently applying the kernel trick. So that means that we still do linear metric learning. It's only that we first apply a nonlinear projection into the kernel space, and there then the rest proceeds as I just showed by means of linear mapping. So kernel is this inner product space, this scalar product that I compute here after doing a projection with this projection function phi. There's projections of the individual training points, x1 to xn, I can just assemble in a large matrix. And then I essentially replace the matrix M that I had with the projections of another matrix. And the beauty, as you know from the kernel trick, is that in what you see in the second row from the bottom, the phi matrix, the phi projections have eventually disappeared. Now we're just dealing with the kernel matrices, and that we can handle. But we need a large number of parameters. We can only work with inner products. The technical problems of kernel methods also exist in that kind of approach. And that's why after the day and age of support vector machines, most of us these days are doing deep learning, because these methods actually have been shown to better scale to larger numbers of data. So what we here want is then have a mapping from X over to this embedding space. And in deep metric learning, this mapping function psi is for that reason represented by a neural network, which then leads to a space where we compute the distance using, for instance, Euclidean distances, as we've seen beforehand. Just so you know, in most of the papers on deep learning, you don't see a single function there, but actually a concatenation of two. The first of them being a feature extractor, and the second one then being the mapping over to a metric space. Now, if you want to memorize or remember anything from this talk, then hopefully this slide, because here I'm going to show you deep learning in a nutshell, as compact as I can. So first thing that we want to do is choose the parameterized embedding function. This psi function now has parameters, which are the weights of our neural network. And you want to choose like the design topology of this neural network. And we want to learn these parameters theta. Then you want to choose a distance measure for the embedding space, for instance, Euclidean or any other that you want to go for. And then you gather data and constraints, similarity judgments from a user. Similarities, dissimilarities, things that you want to be apart, and potentially more complicated ranking type triplets constraints. You want two samples being closer together than to another, which nicely works in topological spaces. And then you optimize the parameters of this neural network so that the resulting projection that you see here best agrees with the judgments that you're provided, given a loss function that we still have to define and potentially an additional regularization, which makes sure that our function just doesn't go out of bounds. And with that, I want to kind of conclude by showing you the main topics that exist in deep metric learning, which then will be deepened in the following talks by Timo, Jenny, and so on. The first is the objective function, and there a lot of different objectives have been proposed. Typically, they're ranking-based approaches where you are, as I've shown beforehand, provided with triplets, an anchor point, and a positive, which you want to be closer to the anchor than the negative, which you see here expressed typically by a contrastive function with an additional margin, gamma. There's extensions to multiple positives and multiple negatives, like multisimilarity loss. There's approaches that don't just measure the similarities between the points, but between the nearest neighbors of these points, and that these are proxy-based approaches. So you're essentially measuring the probability that xi chooses pi as nearest neighbor, normalized with a set of all proxy neighbors to p, which you see expressed by the exponential on the right-hand side. And then there are simpler functions, the humble classification-based approaches. They're inferior, but at the same time, they allow you to scale to millions of training points because they're more effective, better scaling there. For that reason, you might also consider them in scenarios where you have lots of data provided. Secondly, sampling matters. If you're looking at triplet relationships, we have a cube number of triplet relationships provided. And if we, in deep learning, want to consider big data to the power 3 is big data. It is clear that we cannot shuffle all of that into our learning approach. And there's been lots of sampling approaches considered, which essentially ask this question: what is the negative xk here that I should choose for an anchor and a positive? Or, so that would be like finding hard negatives, semi-hard negatives, and so on, potentially also mining the positives. Third, ensemble methods. Why just go for a single metric? Why not combine several ones together, several local embeddings together, for instance, into then one global embedding? And lastly, and that's the last thing that I want to hear, last point that I want to make, generalization. We're typically in metric learning in an IID scenario. That scenario is well defined. You provided the classes, which you see towards your left, and you want to then make judgments over additional samples that come exactly from this distribution, which you see on your left. But what if the test data comes from a different distribution? We have a hard time making these predictions. The discriminative approach you see here explained is just separating the train class 1 and 2 from another, and those test classes would then end up on the other end. Not too good. Timo, for instance, has investigated sharing. Others have investigated other approaches there, and all of that with the aim to improve generalization. So let me wrap up. Similarity and measuring similarity is the basis for numerous tasks out there in computer vision and machine learning. learning such a richly structured representation, especially in a low-dimensional embedding space, is very important for fine-grained relationships. Metric learning in that case comes in different granularities, being linear up to like highly nonlinear methods. And the main directions these days are on the objective function, the sampling strategies that you might consider, ensembles that you might utilize to improve the performance, and lastly, generalization. And that, I believe, is really like the holy grail, capturing the semantic similarity of our input space for all of these follow-up tasks. So thank you for your attention. I'm happy to answer any questions if you have. Yeah.
So you spoke about the variance to somewhat different languages.
True. Can you say that again?
In the beginning of the presentation, you spoke about the invariance, different angles of an object while we're learning the measurement.
Mm-hmm.
And you saw a few examples. Maybe you can, is it going to be discussed later, or maybe we can discuss right now? What is the relationship between what type of augmentation we decide to use for how we learn arithmetic, or what type of invariance we learn arithmetic?
Yeah. So you're asking what type of augmentations to utilize to get the invariances?
Right. So like wouldn't the invariances be biased towards the kind of augmentation we use? Like if we decide to like augment or compare between different angles of an object with different classes.
Right. Thanks. So of course you can. So typically there are two ways to go about. One is learning the invariances directly from the data, but if data is scarce, to learn these invariances, you typically require some inductive biases, like augmentation strategies, for instance. And the moment that you throw them at your problem, it heavily depends on what augmentations you have chosen. So if you go for changing the color, for instance, to make it invariant there, that is an inductive bias, and you better make sure that it's pushing your embedding in the direction that you actually would want it to go. The worst thing would be that color actually matters and you made it color invariant. I mean, then you lost it, right? So if you want to recognize the traffic sign, like a traffic light, red and green, separate them from another, and you make your approach colorblind, that would be bad. So choosing the right augmentations for that reason is really critical, and later talks will now in detail also focus on this aspect. Any further questions? Yes, that's not the case. Timo?
Yeah, thanks, Björn, for your introduction to similarity learning. During my talk, we'll try to stay close to the microphone because it's quite insensitive. So yeah, if you don't hear anything, just raise your hand or whatever. Yeah, so after the general introduction to similarity learning, I would now like to start with the talks about like how to train modern deep metric learning models, the whole pipeline, and basically some of the stuff Björn covered, like important concepts and components. And to start, I would first like to start with a short wrap up of what the typical DML training model setup looks like. So we basically want to learn a representation phi of x, which reflects semantic similarity d within our training distribution x. Yeah, so we basically want to put those images together in our feature space, which are supposed to be similar while pushing others far away from them. And like Björn already mentioned, typically we have class-based annotations as an inductive bias to learn these similarities. And our models typically consist of an encoder F capturing tunnel features, and the embedding space phi is then actually realized as a single fully connected layer stacked on top of directly on the encoder. And for regularization purposes, our embedding space is typically constrained to the unit hypersphere in the d-dimensional embedding space. Yeah, so in order to train such models, one can, let's say, divide or categorize the current landscape of DML models into 5 categories, or like 6 if we consider like the outliers, the others. with the most natural one being ranking-based DML that Björn already mentioned briefly. And there's also classification-based DML, meaning we want to use the standard softmax formulations that everyone knows from classification in order to learn our structured feature space. There's proxy-based DML, which is today one of the most powerful approaches. And there's also contextual DML, which is basically an extension and advancement of ranking-based approaches. And as well as ensemble-based DML, which we will also cover here. And like I said, there's also like the others category when we cannot really fit one model or approach into one of those, let's say, 5 categories that will be covered in the next 2 talks. And in this talk, I will now first cover the ranking-based DML, the classification-based DML, and the ensemble-based DML category. So let's dive in with ranking-based DML. Well, like already mentioned multiple times now, we basically want to learn in informative embedding space that requires us basically to arrange our data under the representation, under the mapping phi of x, meaning we want to order our samples in embedding space such that the similarity that we want to achieve makes sense in this embedding space. And naively, we can call it like rearrangement, since we basically order the data in the embedding space phi. And such an ordering can naturally be formulated by basic learning constraints, meaning we want to have something like bit A is closer to B than C, or in the language of DML or images, we want to have a positive closer to a given anchor image due to being from the same class than a negative anchor image due to being from a different class. And yeah, leveraging lots of these constraints will actually lead to exactly what you want to have. So this, I think a very intuitive approach to deep metric learning, and was basically also one of the first approaches which really take off. And we introduced, let's say, metric learning into the deep learning era.
I mean, I was co-casting with Jordan, and we didn't know where to look. How you can coordinate those? Possible?
Right. We have a guest speaker apparently.
Yeah. Possible. It was quite messy, but it can get even messier in Socotra. Like no one deleted.
It very naturally formulates exactly what you want to have, meaning A is closer to B than C by means of triplets A, P, and N. And the most basic formulation that you want to have is basically optimize the distance between the similar images, meaning make them their distance close in the embedding space, and maximize the distance between dissimilar images, or simply minimize the difference between the both. And in order to avoid the model overly focusing on the negative part, meaning pushing negative samples far apart from their counterparts due to class differences, we typically regularize the whole loss function by using a Hinge formulation, meaning we only optimize the difference between the 2 relations up to a certain threshold, which we basically define by a certain margin parameter, meaning we want the distance of a positive to an anchor being at least closer than a negative by a margin parameter alpha. And this formulation, like I already said, is, I guess, quite familiar to maybe a lot of you, since it's also heavily used in other fields as well. And it's a long-standing loss also, which also have been used in the classical era of metric learning. Another more recent loss, and which is was quite influential at the time, is the margin loss by Hu et al. In 2017, and this paper we're also gonna come later today again in the sampling section. But the margin loss, besides for reformulating the triplet loss a little bit, also introduced the learnable margin parameter, meaning that we're not only having the standard fixed margin parameter alpha, but also we have a now learnable parameter that we can, besides adjusting it in the general level, meaning using some beta 0, we can also add a class dependent or even image dependent part in order to modify or really make the whole embedding space flexible. And during optimization, we typically perform a joint-wise optimization, meaning we use all the margin-based constraints and simply wait with the learnable margin parameters. However, in practice, we typically drop the last part since learning sensible or meaningful margins based on single images is just not really feasible, and typically also only leads to overfitting effects in the model. So we typically drop the last term and only go for the class-dependent part. Yeah, so those two losses are basically like prominent examples of triplet-based formulations. And during optimization, we typically in our batch use each sample once to form such a triplet, meaning that we basically, if the batch size is given by B, we have a linear number of relations for optimization linear in B. And evidently, we actually would also have up to have B squared relations. So a straightforward extension was then to somehow try to maximize the information that we squeeze out of our batch, meaning that we at least want to use all those negative samples that we can get for a given anchor and positive. And one of the first formulations taken, like introducing these concepts, was the lifted structures feature embedding loss, where we have here denoted in green the part of where we basically minimize the distance between the anchor and the positive, and denoted in red, we have basically maximize all the distances from the anchor to the negatives in the batch and the positive to all the negatives in the batch. And additionally, they also introduce the exponential weighting, meaning that we want to further, like more strongly focus on those negatives which violate the ranking constraints, meaning those negatives which are close to samples from different classes, which is also later covered in the negative sampling section. Another loss, which is still very powerful today, which means it's a really strong baseline, easy to use, and widely used in the field of DML, is the multi-similarity loss, which basically follows a similar concept. Again, here in green, we basically want to leverage multiple anchor to its positive relations for optimization, and also multiple negative relations to our anchor sample. Additionally, they also introduced some an informative pair mining, meaning that those negatives, for example, which we could consider uninformative, since they're already far away from the positive class, so to say, we can drop them entirely for the optimization of the loss. So they basically mine pairs which follow the formulation, like use only those positives which are less similar to the anchor than the best negative, or only use negatives which are more similar to an anchor than the worst positive. So always like the hardest positive and the worst negative, so to say. Yeah, and like I said, this is like if you want to train the DML model today, this is one could be one of your first go-to choices, since it's nice to train and still powerful. Yeah, so I here basically already touched the topic of mining pairs, meaning like informative of triplets, informative of relations that you want to use for optimizing our model. And like Björn also introduced in his talk, this is a crucial part of a lot of ranking-based formulations, especially triplet-based formulations. And there has been quite some, let's say, way out proposed, since like Björn already said, the premise that we're actually having is that given a data set of n images, we basically have cubically many combinations of triplets that we could potentially use for learning. And with the scale of nowadays data sets, this simply becomes infeasible to use all of them for training. But in turn, you can also notice quite quickly that during training, lots of those triplets are actually uninformative, since they're quite quickly being fulfilled, meaning those constraints are correct and those, let's say, provide any more meaningful learning signal to our model. So the question really boils then down to which negative can be considered informative, which negative should we sample in order to provide our model with still informative training signals. And there has been two heuristic approaches, which are most widely used today and which works quite well in practice. The first one, again, a very prominent concept in machine learning and vision in general, being hard negative mining, which is not only used in, for example, deep metric learning, but also in object detection, segmentation, and a lot of other fields. So the concept is basically in hard negative mining, always go for the sample for the negative that is hardest for a given positive anchor, meaning the one that violates the ordering constraint the most. Or in its, let's say, semi-hard, more softened variation, where we basically constrain those hard negatives to be at still further than the worst positive from a given anchor, so to say. While this heuristic, the sample heuristic works quite well, our models at the end of training especially sometimes suffer from unstable gradients to only focusing on hard negatives only, meaning that either we maybe only consider a certain subset of our training data, meaning we lose out of information, or we maybe also our model suffers from noise since we don't know where these super hard negatives are coming from. And a way down to that, which is up even today, let's say among sampling strategies, the most widely used, and I guess the best trade-off between simplicity and payout, so to say, is the distance-weighted sampling, again, proposed by Wood 2017 that we already encountered with the marginal loss. So instead of always going for the negative sampling and the hardest negative sampling only, we basically formulate a sampling distribution over our negatives for a given anchor, and the sampling distribution is basically based on the distance from a negative to the anchor itself. And the question then basically is what is a sensible distribution to choose? What should we use in order to parameterize our sample distribution? And the answer is to basically encounter the overly hard unstable gradients from the overly hard samples, is basically try to uniformly sample from the whole range of difficulty, the whole range of path distances that you can actually have from a negative to an anchor sample. However, the issue here is that naively going for always like uniformly sampling from the whole range of distances will lead, especially if we have hyperdimensional embedding spaces, will lead to increasing sampling bias, since uniform distribution on the hypersphere for large dimensionalities is actually strongly biased towards a very narrow interval of large distances in general, meaning we would actually go for very, let's say, easy negatives, and thereby getting a very uninformative model only. And the natural solution to that is basically to find the uniform distribution, or to formulate the uniform distribution on the hypersphere, which can be analytically formulated, and then inversely sample from that in order to basically weigh down the negatives coming from this biased range of distances, and more strongly focus on those negatives coming from the tails of this distribution. And this in practice works very well, it's easily implemented, and is also kind of robust. So an example here to compare the distance, the sampling heuristics is basically that with, let's say, the blue diamonds, we have the distance weighted sample. You can really see that from the whole range of distances given on the x-axis, we basically sample uniformly from the distances, where we, in the case of hard negative or semi-hard negative mining, we really focus on the very small distances, while going for the naive sampling, the naive uniform distribution over the distance interval leads to overly sampling from this very narrow interval of very easy and uninformative negatives. So the distance-weighted sampling is, again, if you want to train your triplet-based DML model, this is the way to go, the first shot you should do. However, those approaches are still heuristic, meaning that are basically disconnected from our model. So as we learn from, for example, the field of curriculum learning, our models sometimes requires different, let's say, learning signals at different stages of optimization. A common principle in curriculum learning is, for example, that at the beginning we should go for more it's easier examples, while at the later stages, when our model is already kind of powerful, we will present it with the more harder cases. Although this is not entirely, this is like an intuition and had also been disproved, so it's not really, we cannot really guess what kind of training signals are needed during the optimization. And the question is, okay, how can we formulate a distribution over the sampling, a sample distribution, which basically adapts to the needs of our model. And the PATS method, the policy adapted sampling strategy, basically learns exactly such a formulation, again, in contrast with the heuristics, where we basically manually set or guess some kind of weighting, the training learning signal that we want to go for. Now we can learn the signal, the sampling distribution, by means of first formulating or parameterizing our sampling distribution P over the interval of the distances on the hypersphere. by the equisized binning, where each bin basically represents the sampling probability of negatives falling into that bin. And having such a flexible parameterization, we now can start to learn it, to adapt it to the to every stage of training during optimization of our model by using, for example, reinforcement learning as a strategy, where we basically learn a policy network pi to propose changes to our sampling distribution such that the performance is always maximized on a held out validation set, which is not used for optimizing our model, meaning we really are even going for generalization performance here, since we're basically making sure that the training signal are always leading to performance gains on a validation set that has not been used for training our model. And for reinforcement learning, the rewards are basically defined by the performance gains. And yeah, so this works quite well, although it may be too computational heavy for some approaches. But if you really want to squeeze out like the last bit of your training a triplet-based model, the PETS method is definitely the way to go. Yeah, so this basically concludes the part about ranking-based DML. And I would now like to come to the second category, which is classification-based DML. Classification-based DML, as everyone can imagine, is based on, okay, do you see, is there something hidden here? Can I close that one? Okay. So, yeah, I mean, as I guess most of you were guessing, so this is basically, we're basically trying to make use of the classical softmax formulation, the classical softmax loss, to learn a DML model, since classification is actually what we're going for by like pushing the samples from the same classes together in the embedding space and pushing samples away in the embedding space, which come from different loss classes. This is actually a classification-based formulation. So going for softmax formulations is actually a natural thing to do. However, naive using the softmax function actually turns out to be not too successful in DML. And the question is, how can we adapt it to our DML problem? Well, okay. The first thing that we can recognize, that is kind of well known, is that the rows of the weight matrix of our linear function basically represent mean representations for each class, meaning that when we compare a sample to the rows of the weight matrix during the classification process, we basically compare the sample to whole chunks of our training distribution immediately, like at once. And just as a side note, this concept basically also gave rise to the very powerful DML category of proxy-based learning, which we will come to in the next talk. But here I just want to state the connection between classification-based DML and proxy-based DML. And yeah, as in one of the advantages of those these proxy-based models is that we can basically alleviate the sampling problem by not going for individual or those, like, let's say, cubically stated individual relationships between our samples, but we basically compare each sample immediately to the class means and thereby by entire modes of our training distribution. And so how do we turn the classification-based softmax function, or how do we adapt it to the DML problem? Well, the paper by Seidenschwarz basically showed how to turn classification into a competitive baseline by following two basic concepts, or by let's say, using two natural techniques. The first one being, which is the standard in DML, regularizing the embedding space to the hypersphere, and thereby normalizing our embeddings and the rows of the weight matrix as well. And the second one using the temporal scaling parameter in order to sharpen the gradients of the classification of this distance loss function, and then thereby to enforce more compact intra-class clusters, and also pushing the clusters of different classes in the embedding space further away. And to draw connections to other fields as well, the temporal scaling is actually a well-known tool, or let's say trick, in order to further improve performance in a lot of other models. For example, self-supervised contrastive learning, you will also have encountered this tau parameter. Yeah, this function, or this approach is then called normalized softmax loss, And as Said showed, was at that time competitive to the DML models of that time, so to say, of that time in 3 years ago. But the classification-based approach that we would like to go for is the one that is heavily used in face recognition, which is basically formulating the DML loss, our objective function, not by means of, let's say, the standard distances that we were facing so far, meaning Euclidean distances or the cosine distance in our softmax function, but explicitly formulating the objective function on the angles between our samples on the hypersphere. And like I said, this is a very popular formulation in the face recognition community, since you're able to compress your classes in embedding space by quite a bit. And in face recognition, typically each individual is its own class, meaning there's not too much intra-class variation. And using this formulation, we can really nicely compress those, let's say, classes of individuals into very dense areas in the embedding space. And in order to derive the loss function, we can basically first identify the inner product in the softmax, and then replace it with its reformulation based on the cosine of the angle between, here, let's say in general terms, x and y, or in this case, between the sample protection, the sample embedding, and the rows of the weight matrix. And then again, we identify the norms over the respective embeddings here, and following standard DML conventions, we can then constrain the rows of the weight matrix again to have unit norm, and as it was first proposed, the embeddings to a more general parameter S. And now we already identified that the loss function, our objective function, is really immediately hinging on the angles between our embeddings and the let's say class representations. And yeah, now then what the level is left to do is basically optimizing this whole expression. And we can even also use the standard tricks that we already encountered, like for example, introducing a marginal parameter beta in this time, similar to the ranking-based category basically. So now the angle is basically defined in the margin is basically defined in the angular space, meaning we have here depicted in this image, we make sure that the angle between the classes, so to say, suffices a certain threshold. Yeah. Again, we can nicely visualize what happens if we increase the margin. Here, starting from the left, from the standard margin, median 1, meaning we have no margin, with the small margin. We have quite an overlap between the negative and positive distances, denoted by the red and blue distribution. And as the margin parameter increases, we are actually able to increase the first make our classes in the embedding space even more compact, but at the same time increase the margins between the classes. And these plots have been taken from the respective papers, since they're really nice. And that's basically my part on classification-based DML. So this is, like I said, heavily used in the face recognition community. And let's say in the more general or less specialized applications, there's a good bunch of different categories that have been used. And the next one that I would like to talk about, and the final one of this talk, is basically the ensemble-based DML category, where we basically make use of for example, baselines from the ranking-based DML and turn them into powerful DML models following ensembling approaches. So what is the basic principle here? We have our, let's say, our single DML model consisting of the encoder F and the fully connected embedding space phi. And we typically optimize it by means of some discriminative loss function. And the standard principle of ensemble learning is basically, in order to make your model more robust, learn more models than just one, let's say, k independent models, and aggregate their predictions, aggregate in DML terms, aggregate on their representations into a single global representations. And thereby we assume that basically, let's say, mistakes or errors made by one model is averaged out or compensated by the other models. Like I said, ensemble methods is a very common topic. For example, in Kaggle challenges, lots of the best performing models are typically ensemble models to really squeeze out the last bit of performance. And This naive way of ensembling, however, comes with computational burden, meaning if we optimize k-independent models, we have to train k-independent, perform k-independent training runs, and which means either we have to allocate more resources or more time. And a common way out here is basically to identify that the encoder function f typically encodes quite general features, which in general are shared or would be shared between the different learners, especially low-level features. And so we basically turn the learners now into like different embedding heads, meaning that we have different embedding spaces which are trained concurrently while being connected to the same feature encoder f, and thereby mitigating the computation overhead. And each learner basically benefits from the features learned by the others, since everything is fused into a single shared encoder f. And yeah, this approach has first been introduced by Opitz et al., the Beer paper. And they additionally proposed, instead of just letting each learner learn by itself, whatever it wants, to perform an implicit specialization of each learner to certain features of our training distribution by following a gradient boosting strategy. Again, gradient boosting is also maybe a well-known technique, for example, random forest or gradient boosting trees, or other boost approaches in general. And they basically used it in the same way by rearranging, or like by using the errors made by one learner to re-rate the sample contributions while optimizing the next learner, and thereby sequentially making up for the errors of the previous model, so the previous learner, so to say. And additionally to this implicit specialization, they also applied a very commonly used technique in DML, ensemble-based DML, which is the adversarial decorrelation, where we basically want to reduce the overlap in features being learned by two learners by decorrelating their feature spaces. And since decorrelation is not a trivial problem, they basically formulated a nice, let's say, way how to achieve that by means of introducing a projection network, which typically consists of, let's say, 2 or 3 hidden layers. And the task of this projection network is basically to find a mapping from learner J to I, meaning to establish a decorrelation actually between the learner feature, the embedding spaces. And in order to achieve the decorrelation, then we simply we flip the gradients to actually go for the opposite direction and going for decorrelation. And this adversarial decorrelation is performing quite well and is heavily used whenever you or like quite often if you encounter an ensemble-based models. And yeah, so this approach, like initially started with an implicit specialization of features by means of the gradient boosting strategy. And we can even make this more implicit by a divide and conquer strategy proposed by Seidenschwarz et al., where they basically implicitly first partition the training distribution into different disjoint subsets of training samples. And on each sample, we then ideally learn an individual learner, which captures the particular mode that is it's supposed to be trained on. And then in the end, in the congruent stage, we again aggregate all the learners into one global embedding, which is basically just a combination of our individual ensemble heads. And the question is, how do we partition our training data? We could do it even randomly, but this typically only leads to each learner having a similar let's say, training distribution. And but the idea is basically we identified that our training distribution consists of different modes. For example, let's say different class modes, which would give rise to an approach where we would distribute the classes, entire classes among learners. However, in a more sensible way to go is to go for, let's say, a semantic partitioning, where the divide and conquer strategy, or the paper by Seidenschwarz et al. Proposed to use some general intermediate feature representation, for example, the ImageNet pre-training of our model, to perform a clustering on top of that, and thereby really splitting or partitioning our training data by means of the more of, let's say, a semantic on semantic grounds. And yeah, aggregation, like I said, then is basically performed by concatenating the individual learners into a global learner. And the authors also proposed the post-processing to basically fix the consistency issue between the embedding spaces by just performing a few epochs of a global fine-tuning of the concatenated global feature representations. the authors basically showed that with each learner added up to a certain saturation, performance is actually increased, meaning that specializing our learners to certain parts of the training distribution is actually very beneficial to achieve both specialization and diversity of features. The authors then also came up with a follow-up work where they basically introduced a hierarchical divide and conquer strategy, meaning that we perform a sequential splitting instead of going of the global splitting from the right away. And yeah, so far we're basically going for discriminative learners only. So if I go back and if we recall here, we basically see that each of the learners are basically optimized using a class discriminative approach, which in principle always leads to more or less the same features, meaning features which are very specialized in separating between classes. And if we have lots of classes, those features can get very, very specialized to our training distribution. And so yes, basically can be in terms of, let's say, diversification, can we find complementary features that we can like fuse in our model, which are maybe also more robust in terms of distribution shifts to training distributions. For example, can we also maybe learn explicitly capture about color, shape, or viewpoints, which are typically features or like features or data which we get invariant to, like Björn already mentioned. And the first paper the first work to like follow this concept and address this or try to come up with a solution of diversifying the features being learned during training is defining intra-class characteristics by Roth et al. And the idea here is basically similar to the divide and conquer strategy, that we try to find surrogate labels which are complementary to the class labels by first performing a clustering by means of some intermediate general representation of our model. And in order to explicitly make those features, let's say, less informative about the class information, they also subtracted the class mean from each class cluster to basically performing some feature standardization, and thereby actually having similar, very like, let's say, general features which we can cluster to get our surrogate labels that we can then use to perform, let's say, a multitask learning problem by having both discriminative features focusing on separating between classes and intra-class features focusing on learning intra-class characteristics, meaning features that might be shared between classes and that get basically discarded during only class discriminative learning. And to simplify this, basically, we can also even drop this clustering step and explicitly go for positive relations, meaning anchor to positive relationships across classes by sampling all of our triplet constituents from different classes. And this basically leads to learning shared features, which are similar to, which follow a similar concept like the intra-class characteristics, but in this case really are focusing on only features that are learned across class boundaries. While, for example, in the surrogate features, there might still be those clustering might still be biased towards certain classes and thereby not really going all the way. And we basically also showed that looking at the embedding space phi2 in this case, the shared embedding space, we can really see that there are clusters forming, for example, focusing on the viewpoint across classes, meaning different car brands or like cars of different brands facing the same direction, or even cars of different brands just being related by their color. And this concept turned out to be really powerful, especially when it comes to out-of-distribution generalization. And but this is not where we would stop here. We can even go even further, since I already said this basically formulates a multitask learning problem. And in the follow-up work, we basically extended this to formulating multiple or even more learning problems. First, using the ones that we just saw, the class discriminative features and the class shared features. And additionally, we can also make use of this simple sampling trick, but this time sampling sampling all the constituents of triplets from the same class, thereby achieving a certain or like enhancing intra-class variation, intra-class variance, and additionally also formulating a learning head, which is optimized based on standard contrastive self-supervised learning. However, we additionally also optimized or adapted the loss function to the task of DML. And if you want to have more details here, I'd suggest a look in the paper, since this adaptation was quite crucial, but it's now getting too technical and too far into the talk. But yeah, as you can see, we really form an ensemble here, a multitask learning problem, and basically show that with each task added, indeed performance of the model is increasing, which might even might suggest that formulating even more different complementary tasks would make our model even more robust, up to the point where we hopefully capture all the samples of our training distribution and thereby making it as robust as possible out of distribution chains. And yeah, with this slide, I basically come to the end of this first talk on the first three categories, meaning ranking, classification, ensemble-based DML. And yeah, thanks for your attention. I'm happy to take questions. And in the next talk, we're then going to cover the next talk after the coffee break. We're going to cover the remaining two categories, so stay tuned. Thanks.
Thank you so much. I had a question. You made an assumption in one of the first slides about the embedded unit sphere at two-dimensional space. What is the main reason and benefits of that assumption?
One reason is that you basically bind the errors of your model that is having by bounding the distances between the samples in your embedding space, and this is basically leading to very stable gradients. So this is a very standard thing to do. And yeah, I think the main explanation is again having stable gradients, as so often in deep learning. Yeah. Hello.
Provide any intuition on the merits of choosing one of these types of triplet loss versus the classification-based loss. It started when we first started doing some of this stuff. It was started with classification loss, and then triplet loss came out, and that kind of took over everything for a while. Now it seems like from full circle back to at least the base definition back to classification loss. So I was curious if you had any intuition on kind of just how to choose which one to focus on, and maybe also where you see things going in the future.
Yeah. So indeed, the two things basically are converging right now. In a lot of models, you see that also in classification, you start regularizing your embedding space to the hypersphere and so on. And why there's not a very definite answer why this is one is clearly better than the other, why, although you see it let's say empirically. One intuition basically is that we're basically having a very fine-grained representation learning problem here, meaning the differences between classes are very, very small. And thereby going for, instead of optimizing, let's say, optimizing sample, the distances of a sample with a class representation by means of the inner product only, going for really the individual representation between samples seems to be very beneficial. But I agree that now we basically bounce back a bit by seeing more or less a convergence of different techniques, which are very beneficial for both classification and metric learning as well. And you can even spin this further, going to few-shot learning and so on. So in the end, it seems like the holy grail, the best performing way, the best way you can go for is regularizing your embedding space to the hypersphere and then applying a lot of tricks there. But really different, a lot of fields basically converge to this. Also, for example, self-supervised contrastive learning. Again, you have your manifold constraint to the hypersphere. And yeah, I guess so. Let's say findings of different approaches basically lead to an unusual, let's say, advance of the different fields. Yes. Unfortunately, yeah. I'm sorry, I didn't get the last part of the question. I'm really sorry. Meta learning is, for example, often used also in few-shot learning, where you try to make your model very adaptive to new classes. And as I already said, the two fields are basically converging there. For example, in fusion learning, there are models which shows that like a good embedding space is all you need in order to achieve also the good adaptation to few examples, like to the few examples that you may get from your test distribution for out of this generalization. So yeah, I'd say, like I said, I mean, in the end, I think it's across different fields, finding a best way to characterize your embedding space to learn one strong manifold with which is very informative about your data. This is basically what you want to have. And all the different fields approach it from different directions. Again, there is more or less a convergence nowadays. So this is my take on that. Yeah.
Hi, can you go back to the classification, please?
Like just yell stop.
This you apply if you don't have hard classes.
I'm sorry, I didn't really get your question. I will come. So the question basically, if this can be applied, if there is no class information at all, and indeed this basically is exactly like is very close to the noise info in CE loss, the noise contrastive estimation, where we basically replace the rates of the road matrix with individual samples only, and this basically gives rise to contrastive learning, which is a very powerful self-supervised learning framework, and which is, I guess, still the leading framework in self-supervised learning. So yes, you can do it without having label information by basically only using the training distribution itself, and you basically, in order to get your like positive to anchor relations, you resort to augmentations of your samples. So just as an example that we're talking about here, basically right down there. I'm not sure if you see my cursor. Oh, you do. Okay, cool. So you basically choose simply a sample as your anchor, and you construct the positive artificially by using some augmentation of it, and then you could basically immediately apply this softmax-based formulation. But again, this is like there's a huge field revolving around this, and this is contrastive learning. Any more questions? If not, I mean, if there are questions, like I said, later on, we will have an open questioning phase, so to say. So yeah, you can come again and ask all your questions until you're happy. So thanks, and this is it for now, and now we can go to a coffee break.
And we'll reconvene at 1:15.
Okay, so I'm going to talk to, like, first, actually, sorry for not being able to be at New Orleans, but I just broke my leg, and so couldn't make the arrangements in time. But thanks for having me, like, to have this talk virtually. And today I'm going to talk about, of course, metric learning, but we're going to go a bit away from like contrastive and triplet loss, and to see, like, are there any ways to use more or less the entire samples at the minibest, like all the relations between them at the same time. And like we saw, like in the previous talk, like a lot of things about the triplet losses. Oh, this is actually annoying. So now you probably see this better. So we saw like that one of the problems with triplet loss is that just the number of triplets is like exponentially large. It's like really large. So it's actually like for, if you have like your data set like n images, then the number of triplets is more or less big O of n to the power of 3. The other problem is that you're actually not using your data very efficiently. So like here, for example, we have like this triplet of an anchor, a positive and a negative image. And we see that despite that we have like 3 images, we are using only 2 relations between them. Now, what happens is like, if you have like, for example, a larger minibest, for example, here we have like 9 images, but still we're using for each triplet, like just 2 relations between the data. So in this case, like despite that we have 9 images, we're using only 6 relations. And in general, if you have like n triplets, and the number of relations the triplet loss uses is 2 and divided by 3. So you see that you're kind of somehow not using your data efficiently, like you're kind of throwing a lot of information that contains here. For example, we see that this anchor here like contains connection with only those 2 images, but it's ignoring everything else on the mini batch. And then the question is, are there like better ways of doing this? So could we do something like this where we use more or less all the relations in the mini batch? So in this case, you're kind of using, if you have like n images, you're using big O of n square relations. And in many ways, you can consider your relation as your data. So like not using all this relation here, it's kind of equivalent to throwing out your data. And this then has a lot of consequences, including that you need like maybe to train much, much longer. Now, there are ways who do this implicitly and explicitly, and I'm going to go like briefly over a few papers, some from our group, some from completely unrelated groups. Now, I would say that maybe we could like all this like ways of using all the relation of the data in this mini batch could probably classify it into 2 different families. Like the first one, which is also more famous and there are more works there, is this of proxy losses, where instead of directly using your data, you're kind of somehow going to approximate like classes and to use this concept of proxies. And the other family of these methods would be this, what I would call like information propagation losses. And of course, it should be like possible to combine all of them. Indeed, we are going to see a paper that tries to combine both of these approaches. Now, what is the common things of both of these families is that at the end of the day, the final loss that you're going to use is going to be like a variant of softmax with cross entropy. So it's not direct like changing the loss function like what you do in triplet or contrastive loss, that you're coming out with different loss functions, but maybe somehow like changing how like the last step before you're going to compute the loss. Let's start on this, like maybe like starting with proxy losses. But before doing that, I wanted just to chat a bit, like just brief like a couple of slides for a classification loss, which I think deserves to be mentioned because it has been like very influential and seems to work very well in practice, but I didn't know like where to put, because it's clearly a contextual loss that it's using like all information and it's somehow like based into softmax cross entropy, but it's neither a proxy, but it's not exactly like a proxy loss. But the idea here, at least on high level, is very simple. Like we saw, like when you do classification, which as probably you saw in the last talk, like it's possible to just train like classification networks and use those features for deep metric learning. But one thing that has like classification is that one class, it's sent into a single neuron, like at the end of your neural network. So for example, here, like this class is like all the instances of this class to get classified correctly, they would go into the, like, there is just an entry for this class into the softmax. Now this soft triple loss, they did like a kind of a modification when they would allow like one class to go into different like neurons. And this kind of makes sense because of the variance that it's in your data, that like even like you might have one class, but maybe some images of that class are more similar to the other. For example, imagine like this class here, but some images are taken like during the day, while some others are maybe taken during the night. And then like it makes sense to maybe like put them into 2 centers, like to put them into different classes. So what they did like into very high level, and I really encourage you to read the paper, is to have like more or less like a couple of softmaxes. Like you have the embedding. Now, instead of directly connecting your embedding to your softmax layer, for example, in this case, there are like 5 classes here, they would connect this to another layer, which is like a fully connected layers, where like all these images can be like are connected with this here. And now, for example, in this case, more or less like in the image here, the number of units here is like 2 times n, when n is number of classes. Of course, like you could have like more centers than this. Like you could have, for example, 10 centers for every class. In this case, like this layer here, it's going to be like 10n. And then in the end, they kind of have a trick to encourage, like at the end, like all these units of the same loss, they are going to be connected to the final softmax. So in the end, like your loss actually here is just going to be softmax with cross entropy. But this connection here, where like like all these units here get like connected here. So this is kind of allowing the neural network to have like, let's say more, like for every class, it would allow like for images to be connected to more than one unit. So they could be like maybe separated a bit better. And this actually worked pretty well. Like this paper was ICV 2019, and back then it kind of reached state of the art, and it has been like very popular and heavily cited since then. So these were just like briefly to talk about this paper. Now is someone talking? No. Okay. No questions, I assume. All right, we keep that in the end. So now the next thing is like the need for proxies. So let's see like this very simple image here. For example, we have only 2 classes here, and each class, let's say, has like 4 samples. Now, if you want to use like triplet loss, there are like here it's mentioned that there are 48 possible triplets. So one triplet would be this image here with this one. So like, let's say this image is anchor, and then it can have like 1 positive, for example, here. And for this positive, there are 4 possible negatives here. So like just this combination here, it's like 4 possible combinations, like let's say 4 possible triplets. And then for like this anchor with this image here is going to have another 4. So it's like 8. And then here it's another 4 combination. So it's like 12. And then you can change the anchor here, like from here to here. So in the end, like there are 48 possible triplets here. Now, as I mentioned, like this has like a lot of consequences. So how are you going to choose like what are going to be like your triplets? How are you going to choose like between these 48 combinations? And we saw that one possible way is like doing this semi-hard negative mining. But another way that was proposed into a paper, like this idea of proxies, is to approximate your class with a proxy. And now this proxy is essentially something that is like, let's say, a syntactic data point. So it's not really one of the points here, but it's something that represents your class. And for people who haven't heard this idea of proxies, you can imagine this more or less like, for example, the centroid into k-means. You can imagine the centroid into k-means that it's kind of a proxy because it's not really a data point, but it's kind of representing your class. Another idea of proxies would be like just your softmax layer. So when you connect that, you're fully connected. Sorry, when you connect the last layer, your neural network with a softmax layer there, then the weight for a particular class could be considered as the proxy for that class. Now, in this paper, they actually like did something different. They would just initialize like proxies to random numbers, and then just try to learn them as you would learn the other parameters, the other weights of the neural network. And this has like massive consequences because now like here, for example, we see like 1 proxy here and 1 proxy here. So now the possible combinations here, it becomes just 8. Like one would be this image with this proxy, like the positive proxy and the negative proxy. The second would be like this other image, and then this other image. So here we have like 4 combinations, and then 4 we would have like for the other class if you change like the positives with the negatives. So it already drastically lowers the number of possible combinations from 48 that was here to just 8 comparisons here. And actually the algorithm, like how you do this is like very, very simple. Like first of all, you have like your neural networks, you just add these proxies. And for example, you could add, the simplest would be to add like 1 proxy for each class. So for example, in your data set, you have like 100 classes, then you're just going to add like 100 proxies with the dimensionality of what was your feature embedding. So in the end, you're adding a bit of weights, but not too many. For example, if you're using embedding of size 512, you add like have 100 classes, then you're essentially just adding another 51,200 weights, which is more or less nothing compared to the size of your neural network. And then for each mini sample, what would you do? You would have like your anchor image, like this X, and then you're going to sample like, you're going to have like your positive proxy, like Y, and a family of negative proxies. Like for example, for every class, you might sample like proxies for them. And then, so you formulate this triplet that you have, and then the loss function is essentially, you could see that this is just softmax with cross entropy in disguise. So you compute the distance in feature space between your anchor and your positive proxy, and then you just normalize it with all the other proxies. So in the end, this here is just going to be like a number between 0 and 1. And indeed, you could just check here, for example, if the distance between like your anchor and the positive proxy, it's like something very small. For example, let's say it's 0.01. Then if you do like e to the power of minus 0.01, you're going to get like a high number, which is like 0.99. So in many ways, this is just like softmax in classification, and then minus logarithm of your softmax of your, like the entry of the softmax is essentially just the cross entropy loss. So in this way, like you're just changing the loss a bit, and instead of using like only data points, you're also using these proxies. And then you're just computing the gradients with backpropagation, doing gradient descent. So everything else is like in classification losses, the only change is that you're using these proxies. And back then, like when this paper, because it's like pretty old now, I think it's ICV 2017, it was very influential. It was like state of the art. So if you can see like the results were massively improved. For example, here I believe is CARS data set, and the result went like from 58 to 73. Actually, yeah, CARS data set, and here is like CUP data set when there was like a small improvement, but this improvement of 50 points is pretty giant, and like those things don't happen anymore because now the results have improved considerably more, but it was like still a very big step in the right direction. The other nice thing of this proxy loss was that, for example, while before people needed to train their neural networks for like 200-300 epochs to converge, now with this proxy loss, they just needed, like, I believe here they use just 100 epochs, and already you were getting like really awesome results, like at 40 epochs, and it was doing much better than the previous state of the art did in like the first 10 or 20 epochs. Now, this idea of proxies like has been changed a bit recently, and there was like this other awesome paper like proxy anchor loss for deep metric learning when they use proxies, but now they changed a bit the way how they use it. So while before in proxy NCA the anchors was like a data point, like some samples from your data set, and positive and negative samples in the triplet, they were like just proxies. Here they changed. So here the anchor is a proxy, while the positive and negative samples are data points. So maybe you could see like the difference from this image. So here we had like, I believe 3 classes, like the circle, the square, and then this pentagon, I guess. And here you see like there are 3 proxies. Now, like the anchors become proxies and the data points remain like it was before. So here, for example, this would become like a proxy, and then you're just going to sample one positive from your samples from some image that is like to the same class as the proxy, and then one negative for the other class. And more or less, they put like some math which they kind of prove that this is like very, very similar, like the loss is similar to the proxy NCA. So if you check like these, except like some margin and the scaling factor, their losses are identical. But the key difference here in the idea is that while before the proxies were representing like the positive and negative samples, here like in proxy anchor, the proxies are represented like the anchors. So that's also why the name of the paper like proxy anchor loss. And they show that actually training complexity, despite this change, it kind of remains the same as before. So it's just the number of proxies times images per class. And they also show like this image, which is like more or less the same image as in proxy NCA, when we show that now the results get even actually much better, and the convergence now is much faster. So they kind of, instead of like putting epochs, it's like number of minutes, but you can see that you're able now to train the neural networks even faster than it was before with proxy NCA, and also it reaches like really high results. And if you check like high results, just compared, for example, to proxy NCA before, sure, there are some catches. Now they use like higher dimension, but while before the proxy NCA was reaching here like 50, now here it's like 68. Like recall at 1, and the same for CARS. Like the result, for example, here would jump like from 73 to 86, so like really a significant improvement. And when this paper was published, of course, was like state of the art. Now, proxies there is another way, like that I'm going to briefly talk about, like it's possible to combine proxies with label propagation. This is what this tuber is more, when they kind of keep more or less the idea of proxies as it was in the original paper, when the proxies are like their positive, like your positive and negative images. But here they are also going to build a graph, like a similarity graph between your input data. And then they're going to add like some label propagation, which is like a semi-supervised learning method when you're going to spread your information from the labels of some image, of some here actually images to the labels of the other images. And this, what would allow is that now like from like your softmax, for example, is going to give some distribution like here. When you do label propagation, in some ways you're kind of making similar images to become even more similar to each other. And assuming that the similarity graph is like good in the sense that your features are already kind of representative. So more or less you're going to change your probability distribution from something that looks like this to something that is more or less one hot label, because your image is going to get like a lot of information from images that are similar to that image. And those images maybe have like already, I mean, they kind of belong to the same class. So that class is going to affect more the class of this particular image. So in this way, they were able to, actually, I will show here that what happens in the end is that you have like maybe this like feature embedding that looks like this. But if you're doing this label propagation, when you're making similar images to become even more similar to the other, then in the end, you're going to get like something like this, where more or less the proxy is going to influence the other images of that class to become like, to get more or less the same label as the proxy. So if this is done right, you're going to get something like this. And also this, like, I believe it's NeurIPS 2019 or 2020. Yeah, it was actually NeurIPS 2020. And this also kind of significantly improved the results. So if you check to compare, for example, to proxy NCA, again, we have like a similar boost in performance to the proxy anchor loss. So there are actually many more proxy losses, but I just kind of found these three, which I think the first one is, of course, the most influential one. The second one was like state of the art for like quite a long time and really made a massive improvement in the result. And this one that has like a drastically different idea to use like label propagation. And I'm going now to connect like this last paper with information propagation losses, which kind of use similar ideas, but from a classification point of view. And the first one I'm going to mention is this paper from ECV, where I'm one of the authors. And what we did here was actually like, you're going to get, like you're going to sample from a few classes, like in all other metric learning methods. And we're going to feed like this object to some CNN. So this CNN is going to give you like two things, like the embedding, so like features, for example, 512 dimensional features that are going to represent that image. And it's going also to give like your class prediction represented by a softmax distribution. So if you have like, I don't know, 100 classes, then you're going to have here like a vector of size 100, where each entry is going to just mention the probability that this image belongs to this class. Now, we call this like classes prior, because this is what neural networks is going to give you from when each data is considered individually. Now, we're going also to build a similarity matrix, or we could also call that we are going to build a graph when the nodes in the graphs are like your class prior, like the information that you have for to what class belongs each image, and the edges in the graph are represented by the similarity between two images. And I'm going to mention in the next slides, how do we compute this similarity between the images. And then like the key here, so the key in this paper was this like refinement procedure, which is just another word to say about label propagation. So what we are going to do is like to change the labels to propagate the information on the labels from some images to the other images. And then when you're changing this label, when you're applying this label propagation, in other words, this is like changing your softmax distribution to another distribution. where you're kind of considering, so I call this a contextual loss, because here, like, while before the softmax distribution was just based into that particular data point, here in the refinement procedure, you're using all the information in the data set, because you have like this fully connected graph where each node is trying to influence the other nodes. And of course, the more similar two nodes are, the more they are going to affect each other. So in the end, like when we refine your softmax distribution based into the contextual information, then we're just going to apply this cross entropy loss. And like, how do we change, like, how do we refine here the information? Like, we are just going to initialize some of the anchors, some of the images, we're going to initialize them with the ground truth. So we call like this concept anchors, which are like the parallel to the anchors into the triplet loss, and the others is just the softmax distribution. And then for the similarity matrix, like the editor is just the Pearson correlation between two embeddings. So for images I and G, we just extract the features, we compute the Pearson correlation based on this formula, and then we get like what is the similarity between them. So in this story example here, we can see that we have like three images, A, B, C, and we see that C and B are like very similar to each other. Like they have like 0.9 similarity, and C with A and B with A, they are just not like very similar to each other at all. So, and then we also have, for example, we assume that A and B are like anchors. So they have like the ground truth here, while C, we just don't know anything about it. So it's just going to, like the softmax distribution is just going to have like more or less a uniform distribution here. So if you do this process that I mentioned, then A and B will try to influence C, but because B is much more similar to C, that we see that in each iteration, like this class 2, which was the ground truth for image B, now in image C, it's going to get like more and more probability there. So it's going like from 0.25, you do the calculation, it's reached like 39, and at some stage it's going to either converge or to get very similar. It's going, actually it's guaranteed at some stage to converge. And that conversion, assuming that these images are really similar to each other, then it's going to be like a label that is more or less similar to the label of B and very different to the label of A. Now, more mathematically, this is like represented in here. When to propagate information, we have like X is just your, like the label that you get from the softmax distribution, and P is the weight multiplied by the X, by your, so the similarity matrix multiplied by the, like, or in this case, it's like similarity between, for example, between, if you have two images, between those two images, I and J, and multiplied like with prior of X. Now, of course, you're going to sum this because you're not going to do like only between two images, I and J, but you're going to do between I and all the images into your mini batch. So you do like this multiplication, and then you're do another multiplication with the initial prior. And here, like, you're kind of refining your prior to something that now it's affected by all the images into your mini batch. And here we just normalize. So this is just like a normalization to stay again into probability space. So after you do like this, and you do this for several times, so because this is like a dynamic process, which actually has like some game theoretical inspiration, something that it's called like replicated dynamics from evolutionary game theory. But if you do this a few times, you're kind of guaranteed to reach some Nash equilibria where any of, like, all your labels that you have here at this stage are not going to change their preferences anymore, even if you continue this process. For practical purposes, we just keep like the number of like this T, like 5 or 10 or something like this. So a small number that you can do a few iterations, and also it's not that big to not have like optimization problems with backpropagation, so to not have vanishing gradients. But theoretically, this is guaranteed to converge at some point if you do this many times. And then the next thing is that when you do this, so you're just like, in the end, you have like some distribution, you're just going to compute cross entropy over the refined probabilities, and then you just backpropagate. So the nice thing is that almost all the methods, like the proxy method we mentioned before, you're kind of adding new weights, while here there is nothing, like there are no parameters to learn into your group loss. but you can still use this calculation to backpropagate over them. So in the end, despite that you're not learning any new parameters, these are going to heavily influence the gradient for the features. And in the end, in metric learning, like the features are all you care. So in the end, the formulation seems actually similar to softmax cross entropy loss, because you have like some probability distribution, and then you're going to use cross entropy loss. But the way how you're getting this probability distribution is very different to softmax. And on high level, this is like a massive conceptual difference, because before, like for softmax, you were just checking like one data point. You just feed it on your neural network, and then you're going to get like the softmax. While here, you cannot just feed like one data point. You're going to like the distribution for this data point is going to get affected by all the other points that were in the mini batch based into this equation here. So more or less like this is the algorithm. So what I said before, you compute the features, you compute the similarity matrix, you initialize like the priors from the softmax layer, and then you do the iteration, and these two equations are more or less same equations as here, but now written into some vectorized format to have like effective multiplications here. And then in the end, you just compute your loss and compute the derivatives and update the weight. So this part is just like standard. This part is less standard. Here, it's instead of doing softmax, you're just doing this iterative process. And the results were actually pretty good. It was kind of state of the art back then in CV20. There is also kind of comparable in two data sets with proxy anchor, a bit worse here. But they were like pretty good results. And for example, if you compare directly with classification, like if classification loss, we see that we are like maybe 6 points better here, like a few points better here, and a couple of points better here. So it's kind of improving because now you're using into the entire context of your data set instead of only into some image. Like this seems that you're using like all the relation in the mini batch, so you're kind of using more information. This is also boosting the result. And then we show like that you could just train in parallel, like instead of just training one classifier, like one neural network, you can train, for example, 5 of them, and then the results are going to massively improve. So there's no magic into these ensembles, because I believe that there were some other examples that were explained in these talks, but here, and those examples were done like more smartly, like here they are like as naive as possible ensembles. And of course, the mandatory figure compared to proxy NCA, we see that not only the results are much better, but we are also iterating like pretty fast here. The only thing is that proxy NCA, like maybe at the first 10 epochs is going to be a bit better, but at some stage, group loss is going to massively improve over that, and also have like a very fast convergence. So in the end, you can see that if you train for like 40, 50 epochs, then that's all you need. You don't need to train longer. And maybe the more surprising finding that we found in this paper is that this loss, because it's using contextual information, or in which you can consider in other points that you're increasing the number of connections between your data. So it's like equivalent to adding more data. Then it's kind of putting some implicit localization, which kind of makes sense because now you're using more relation. If your relation or your data, it's kind of like using more data. So here, this is like a comparison with proxy NCA. And we see that, for example, this green curve here is like the training curve of proxy NCA, which actually it's it's the curve in the training set, like the accuracy in the training set for proxy NCA, which is higher than that of group loss, like you can see, because group loss is the blue here. But actually the testing accuracy or the validation accuracy, which is the one that kind of matters, like for group loss is much higher. So this one is for group loss here, and here is for proxy NCA. So we see that you're kind of getting some better generalization. Like the training is not as good as for other methods, but your generalization methods, it's like your validation accuracy is much higher. And if you see like this, if you compare the curves on train and testing, you see that for proxy NCA, there was like this massive gap between training and testing, while for group loss here, the gap is much smaller. And for data set, like the gap, there's almost no gap. Like you're getting the same accuracy in training and in validation. So in many ways, this is a kind of implicit regularization that seems that it's maybe the reason why the results are getting so much better. Now, group loss kind of worked pretty well. But I think it has a massive problem. Like in deep learning, we try to learn as much as possible. And we kind of inducting our biases here, like the way how we are changing like these label preferences, like it's just like a label propagation based into some mathematical rules here. Now, can we, like, this actually is one problem, and could we actually improve over this to actually learn, like to make our neural network learn about these preferences? The second conceptual problem that group loss has is that the images are communicated only via their label preferences, only via their label, but they are not using any other information. There's a lot of like rich information into the feature embeddings that the images are just ignoring. Like in their communication, they are just telling each other what label, but they are not telling what features do they have. And we said that maybe we could make like a way of going pure deep learning and like using all the information that we have into both like labels and features, and to communicate them like into a way that the neural network is going to learn like how to communicate, how to spread all this information, or how to propagate all this information. And the way we did this is like via message passing networks. Like we would create like a fully connected graph, same as before when we have like the embeddings, and we also have like the similarity between them. And then we're going to do like k-message passing steps where you're going more or less to change these features, like a feature of an image is to get changed by the features of all the other images into your graph. And of course, the more similar two images are to each other, the more they are going to influence each other. So in the end, you're going to change like these features based into the similarity of these features with the features of the other images. In the end, you're just going to, like, after you do this change, like similar to group loss, where you were changing the label preferences, now you're changing the feature preferences here. You're going to have a fully connected layer, and then you're going to compute your cross entropy loss. So we published this into ICML 21, like last ICML, this paper from Gianni, learning interbatch connection for deep metric learning. And the way how you do this, it's, I mean, you're like we did like this by attention, that images are going to attend like more to images that are from similar classes than from hopefully than to images that are of different classes. So, and of course we're going to learn this attention, but here we just prove like some visualization of how this attention is going to change like the features, or more or less how the features are going to get refined based on the attention that they are like images to each other. Now, if this looks a bit, I mean, it might probably ring a bell that, hey, this is more or less what transformers do, right? Like before in NLP, but also in images, like you make like your neurons kind of attending to, or your features would attend to features that are more similar to each other. For example, if an image, which is like maybe divide into rectangular, then some rectangle, like the feature would probably attend to the features of some other rectangle, which maybe has relevant information. While here, we're not doing like attention between like, for example, parts of an image, but here the attention is done between images. So like this image is not going to attend to itself or in parts of itself, but it's going to attend into the, more or less, this is like the idea. So it kind of looks like transformers, and it looks like transformers because actually it is a transformer. So this part here, I mean, this could easily be implemented by a transformer. So you just get like these features here as your like input, then you just compute like query keys and values. You get this like encoder and decoder into the transformers, and that in the end, you're going to get like some final features to which you're just going to project to like doing softmax and cross entropy loss. So when we published this paper, it was state of the art. I'm not sure if it still is. And like the boost was pretty significant. For example, if you check to proxy and to, for example, group loss, we see that in this data set, for example, in CAB, we improved by 5 points, in cars, like 3-4 points, and also in Stanford, like 5 points or so. If you check to the previous state of the art, like proxy was like half a point in these 2 data sets, and like 1.5 point into the 3rd data set. Now, we did like some interesting visualization. One of them was like the effect of MPN. So here it's like trained with the message passing network, so with the transformer or without it. So we see this image here, and these are like images from the same class. These are images from the other class. So if you don't train like with MPN, then the image is probably still going to attend everywhere. Like this is like just a visualization to where it's going to attend. While on the other case, if we are trained with a single epoch with MPNs, then it's going to learn to attend only in the object from, or actually it's going to learn to attend much more in the images from the same class than from the images from the other classes. And then we also have like the same regularization effect as group plus, but here it's like even more in steroids. Actually, this paper kind of is like group plus in steroids. So it's like doing everything better than was done with group plus, like significantly better. So here we have like the curves of training and testing. We actually see that group plus is having a better result into the training set, but we are doing much better into the validation set. So this is like very interesting probably to see that now the regularization effect seems to be even more significant than before, which kind of again makes sense because before, like it was not learned, like we weren't learning, and like we were only caring about the label preferences, while here we're learning everything and we are sharing also the embedding preferences. And the last thing for this paper is that we saw that you could even use this MPN in inference. And the way how we did this is just like to do like some smart sampling in the inference. So actually, I believe this was the first paper that did MPN in inference. And then like in the conference later, like in last year, there came this non-parametric transformer, which are doing like a similar thing when they're also using the transformers into inference. And we saw that if we do this, we further improve the results. So we had like before 70.3. Now we kind of get like a half a point into the data set if we use the MPN in the difference. Of course, for main comparison, we didn't do this because like it's probably unfair to do something extra compared to the other papers. So all the results here are without using the MPN in inference. And the very last thing of this is that we could do like same as group plus, we could just train like ensembles, and here the improvement gets even bigger. So we saw like before, for example, 2 points improvement here when using ensembles, while here we're getting like 3 points here. And this seems to happen also for the other. Despite that we started with much better result than the group plus, if you're doing ensembles, our ensembles compared to the group plus ensemble is going to perform even better. So more or less, this is my talk. So I explained, I believe, 6 papers into 2 different families that try to use like more relations into the data, or in other words, contextual relation, because be it by just connecting everything in a graph, or by using this idea of proxies that represent classes. And we saw that now, like for most part, you don't need to do any smart sampling, and you're getting like, you actually need to train for much less than with triplet loss. You don't need sampling, and you're getting much higher results. So yeah, thank you for attending my talk, and I apologize because of the timing, I couldn't mention many other awesome papers. We're going to put like in the website of the tutorial a list of other awesome papers that reach pretty high results and have cool ideas. And I also didn't mention anything about the tricks which can improve the loss function. So not by changing anything in the loss function, but by just changing a bit like how are you going to train or how you are going to do the inference. And this actually, it will be covered by Jenny in the next talk. For example, we'd see how you can add like some tricks that would massively improve the results in group loss. This is like a PAM paper, group loss plus, like from this year, or the same, like adding just some training and inference tricks to how you can improve the proxy NCA to something that it's like called proxy NCA plus. So this is going to be covered by Jenny. So yeah, thank you.
Yeah, in this talk, I will actually talk about some things that already popped up in the last talks, also in the questions now, namely best practice DML. And I will also cover, for example, data sets now, evaluation protocols, and like the standard protocol in DML where we also will come back to the embedding dimension then. But maybe let's just start in the beginning with the evaluation. So you've already heard in like Ismail talks popping up those tables and those names of the evaluation protocol metrics. And as you've already learned, like in general, in metric learning, we have like a query and a gallery set. And then we want to retrieve an image from the gallery set that actually shows the same person or class as an image in a query set. And so this is actually called the retrieval. Oh, do you wait? Sorry for the to the virtual participants. I did not share the slides. Now you should see it, I hope. Perfect. Cool. So yeah. And yeah, this thing is actually called retrieval. And so to evaluate this retrieval performance, we can actually compute recall at k. And recall at k is equal to 1 if at least one sample of the same class as the query image is among the top k neighbors. So for example, we have in this 2 rows here, in the first row, recall at 1 is equal to 1 because the first nearest neighbor is the same class as the sample image or query image. And in the second row, we have recall at 1 being equal to 0. And then we take actually a look at all of our query images and average over all images that we have. So for example, in our case here, we would have recall at 1 equal to 0.5. And then for different data sets, we actually use different k because we want to account for the different characteristic of the data sets, which you will see in a few slides. But then a second thing is that there are also data sets that actually have the same query/gallery data set. So it's just one huge data set, and each image in the data set will be used as query image once. So for example, here now the pink image is our query image, and then as next image we could use the next pink image, where always the green images are from the same class. And then if we have this setting, we can actually compute a second thing that is called declustering performance. And for this, we actually use NMI, so normalized mutual information. And you can already see in the bottom left corner, there is this image of this, many embedding vectors, so to say. And you can see that on the right side, it's already nicely clustered and the different colors represent different classes. So the right side of the data set is, so to say, already nicely clustered, but in the left side, we still have a lot of clutter. And then to really quantize this, we first compute k-means embedding on the embedding vectors. And then we compute this, as I already said, normalized mutual information between ground truth clustering and our predicted k-means clustering. And this NMI actually gives us some intuition on how much information do we actually get from our predicted k-means clustering about the ground truth clustering. So those two metrics we can use to kind of evaluate how good our embedding vectors really are or present our data set. And this actually brings us to the data sets. So there are 4 commonly used data sets, and the first one is CAP 200 2011, which has about 12,000 images, 200 classes, and approximately 60 images per class. Then we have CAST dataset, which is similar to CAP dataset, but contains images of CAST, around 16,000 images, 196 classes, and 82 images on average per class. And then we have Stanford Online Products, which is substantially different than the other two because we actually have 120,000 images, so much more. Oh, and actually this is not 120,000 classes here. That's a typo, but it is this, I think, around 22,000 classes, something like this. And on average, 5 images per class. And then InShop dataset, also bigger than the first two ones, but smaller than InShop dataset, and again, only on average 5 images per class. And the first 3 datasets, actually, they all have the same gallery and query dataset. So we can also compute NMI on those datasets. But the last one has a separate query and gallery dataset, so we cannot compute NMI on those datasets and this dataset. But what they all have in common is that the first half of the classes is actually used for training, and the last half of the classes is used for testing. And that the evaluation set is equal to the test set, which might ring some bells in some heads because that is maybe not the optimal setting. But we will come back to this later. And now that we have all those data sets and the metrics again like introduced, we can now again have a look at the table here and to get some feeling on the performance of the different methods. So yeah, you can actually see that last year the performance on CAP dataset was quite good already, but there's still room for improvement. And that, for example, on Stanford Online Product, although it's only 5 images on average per class, recall that one metrics is actually also quite good, which one image pretty good that is of the same class. And I maybe won't go too deep into these numbers because numbers are one thing, but yeah, maybe questioning numbers is also another thing to which we will also come later. But also just to have everything, we also have the numbers of an InShop dataset from last year's paper. And we see that on InShop dataset, actually, we are better even than on the other ones. And in the last year, there also now came some works that used transformer-based architectures or vision transformer-based architectures. And in the very top, you can actually see, you can see again the best numbers from the previous page. So the previous page also did only use like so to say only normal CNNs. And you can see that if we now use vision transformer-based methods, we already get a huge performance improvement on some data sets. And this is partially maybe also because, for example, Vision Transformer S is trained on ImageNet 21K, so a larger ImageNet. But in general, we already see that those from the beginning have a quite higher numbers compared to ResNet 50. And those numbers that I've framed here actually just show the performance on the pre-trained encoders without any training on the downstream task data sets. But yeah, then those papers actually introduced some new things, and we can see that we still have some improvement, but that the biggest improvement actually came from the backbone here. And the same we can see also in the bottom right corner, where we again, in this method that was introduced, that when it uses ResNet 50 as backbone, it achieves 82.8 on SOP, while if it uses Vision Transformer backbone, it achieves way higher numbers. So this is maybe interesting and also good to know if you want to use deep metric learning at some point for any task that you want to solve. And now, coming from this new backbones that I use, we actually take a step back and look at the standard protocol and at which backbones normally are used, and also which embedding dimension normally is used. Because actually, to show that an approach in deep metric learning really improves is really improving the embedding, and has not just only more parameters, the community kind of agreed on several things that we should follow if we want to publish in the area. The first thing is actually data augmentation, and data augmentation that the community agreed on is taking an image and then applying some randomized scaling and aspect ratio scaling, and then cropping to a fixed input size of 227 times 227, and afterwards horizontally flipping. And during testing, we only scale the smaller side to 256 and then apply a center crop. So you can see that during training, we have various different images, like various different augmentations of our images. But if we would apply also different augmentations, we could potentially also increase the performance. But for now, the community agreed on those augmentations. And then in the standard protocol training pipeline, we actually first have our batch sampling, where we first do so-called class balanced sampling mostly, not necessarily. We can also do something different, but this is the most standard thing. And actually what we do is we first sample several classes randomly. So in this case here, the rows, so it would be 3 classes. And then for each class, we sample some random number of samples. So in this case, also 3 samples per class. And by this, we ensure that we kind of have several samples of one class and have good comparison between the classes. Then we feed our images through a backbone CNN, and normally we use BN Inception or ResNet 15. And why we do this is actually if we would use, for example, ResNet 101, we could, of course, out of nowhere get way better performance because we have many more parameters and so on. And so that's why actually BN Inception or ResNet 50 are normally used. And you can see already from the upper table that depending on the backbone CNN, we get also quite different numbers for those 3 backbones that we have a look at here. And those backbones are actually just pre-trained on the on ImageNet, and then some downscaling is applied of the embeddings to 512. You've heard those number already. And we can see that already we have some performance with all backbones, but BN Inception overall achieves the best performance. Nevertheless, as we can see on the lower table again, by now BN Inception and ResNet 50 are actually used equally much, while in the beginning GoogleNet was mainly the way to go. And then we downscale to embedding dimension 512, apply any loss function that we want and any optimizer that we want, and actually try to ensure a fair comparison in the end, especially because of BN Inception or ResNet 50 and the embedding dimension. But of course, like sometimes we just want to get the best performance that we can get and not just follow the training pipeline if we want to apply it for deep metric learning for any other task, for example. And then we can actually apply some tricks that can improve the performance quite a lot. And the first thing that you could do is actually, of course, you could just take larger image crops. And then if you do this, you have the possibility to get more fine-grained features and more fine-grained information about your image. Then another thing is, now we're coming to the embedding dimension explanation finally. You could also use a larger embedding dimension to just get a better performance. But in the beginning of deep metric learning or general in deep metric learning, it's also always about a bit how computationally feasible something is. And as we have in the end to compute the distance between our query image and the whole gallery set, we try not to get like 2 huge dimensions, because of course, if we then compute the distance in a 4 times higher dimension, it takes longer and it's computationally more expensive to compute those embedding dimensions. But actually, in the very beginning, the community more or less started with embedding dimension 64, where always it was the explanation we want to have a feasible complexity computationally, but by now it actually traversed to being 512 as the standard embedding dimension. But as you can see already on this slide here, if we use a higher embedding dimension, we can always improve our performance. Another thing that you can actually do, and that was also already shortly mentioned, is temperature scaling. And we all probably know temperature scaling from the classification task, where we use a temperature larger than 1 to flatten our probability distribution a bit and hinder our network to overfit. But what we could do is actually, we could use a temperature smaller than 1, and by this we could enforce our network to kind of overfit more to our training data. But by this we also enforce our data to spread out, like to be separated even more, which is then again in favor of our idea that we want to have really, really small intra-batch, intra-class distance, but a higher inter-class distance. And although this might sound a bit counterintuitive, actually this paper here showed that they reached quite some performance improvement by just using temperature scaling, where the left column is actually without temperature scaling and the right column is with temperature scaling. And you can see that all of their tricks that they apply in their paper actually also really much profit from this temperature scaling, and that in the end, if they use no temperature scaling or temperature scaling, it makes a difference of 11 points, which is like really a lot. Another thing is that we could think of using something different than average pooling. Because normally if we have a backbone CNN, we have our downsampling of the image size, and in the end we have a given number of channels and a given size of the feature map, and then we apply average pooling to get just a 1 times, for example, 2048 dimensional feature vector. And this average pooling assumes that we get the most out of the average information. But of course, this could mean that we lose this super important bit of information that is stored in the maximum value, because sometimes the maximum value might be more important. And therefore, also a paper tried to just use maximum pooling instead of average pooling, and they found out that actually in many works, maximum pooling would have worked better than average pooling. But then again, of course, we think of, okay, but then we lose all the average information, which is maybe also not the way that we want to go, because there's also something important maybe in that information. And so you can actually also apply so-called mixed pooling, so mix, average, and maximum pooling. And by this, get information from both sources. So from the maximum values that might be super important, but also from the average value that also might be super important. Another trick that we could do is actually so-called beta normalization. And we already had the question in the chat before if normalizing all embedding vectors to the hypersphere is actually a good regularization technique. And in this paper here, they investigated this a bit further and found that actually another thing works best for them. And now if we have a look at those 2 vectors here, then maybe we would say, okay, in the cosine or in the angle distance, we are actually quite close. But if we look at the Euclidean distance, we are actually super far away. And that's why this paper introduced to maybe take a mixture of a normalized vector and a non-normalized vector. So still including the information of the length of the vector into our final feature vector. And they also showed that this brings 1 to 2 points in each data set. Interesting because this was actually super common, so to say, in the beginning, very beginning of metric learning, data post-processing, and namely re-ranking in this case. And this re-ranking is nowadays also quite used a lot in person re-identification, which I will come to in a later talk also shortly. And what we do is that we actually have our final ranking prediction. And then we have a look at our nearest neighbors of the query image and also at the nearest neighbors of the query image itself, of course, and then compare those nearest neighbor sets. And based on this, decide which sample should really be the sample that is closest to the query sample. And this re-ranking normally also is super helpful for person re-identification, and it also can be applied here and could be a, so to say, cheap trick if you want to have really high performance in the application. And finally, the last trick is flip evaluation. So the last trick that I will introduce is the so-called flip evaluation, where you actually take an image, you horizontally flip it, feed both images through your backbone CNN, and then combine both feature vectors. And in theory, in theory, our network should already be able to handle these cases because we also apply random horizontal flipping during training. But still, it gives us some performance
improvement. For any particular type of attack or adversarial examiner, there may be ways that you can come up with a quick
Okay. Okay. Yeah, we had another speaker for a second, so back to our talk.
Parts and relationships between parts, things that are a bit out of fashion now, but I think
let's I unmuted myself again. Okay, so if there's anyone in the remote Zoom session that did not mute himself, please mute yourself. Okay, so back to our tricks again. As I said, in theory, our network should already be able to handle this, but still, it was fine to improve the performance. So, as I said already, you can use all of those tricks. Maybe some more, some less, maybe larger crops. You should maybe not necessarily use also larger embedding dimensions if you want to publish in the deep metric learning field. But always mention what you do and do not sneakily use some tricks and then not mention them in your paper to just ensure a fair evaluation towards previous papers. And ensuring a fair evaluation brings us actually to the next point that we shortly have a look at, and this is actually questioning the evaluation protocol. Because we can ask ourselves the question if the current evaluation tricks are actually good. And have some problems here because, for example, NMI is computed based on k-means clustering, and then in k-means clustering, of course, this depends on the use for the cluster centers in the beginning of the theory. We could use these seeds to tune our NMI metrics to get better results, which of course no one of us should do. And then as a second point, NMI and recall at K are actually not that robust as it would be nice. So for example, if we have a look at those three feature embedding distributions here, we clearly see that the one on the very right side should be definitely the one that has the highest metrics. But if we look at NMI and recall at 1, we actually see that for all of the distributions, both metrics are quite high already. And this, of course, is not what we would want to have. So are there some better evaluation metrics? And the answer is maybe, because there are actually two that could have potential to be used more frequently in the deep metric learning community. So the first one is this so-called R precision, where we actually have big R being the total numbers of references for a given query. and small r being the number of references of the same class in our R and N set. So in our number of references nearest neighbor set. And you can see that both rows are actually evaluated with the same number, which is still not perfect, but still maybe a step in the right direction. And then there is this other method or other metrics that is called MAP at R that computes the precision at every point in our R nearest neighbor set, so big R nearest neighbor set. And if at position I, there is actually an image of the same class, we take the precision at that position and sum it to all previous precision values. And if there is not an image of the same class at position I, we just add 0. And by this, we actually take into account how many samples of the same class we have in our nearest neighbor set, and also at which position they specifically are. So the more samples of the same class that are in the beginning of the nearest neighbor set, the better the metric. And it turns out that this metric actually represents the so-called real performance, or at least performance that we would say is good by visual inspection. Turns out that this mirrors it a bit better. And another thing that we can question in the evaluation protocol, and that maybe already rang some whistles before when I mentioned is that we currently actually train with test set feedback. So during training, we actually evaluate on the test set classes, and then by this potentially overfit to the test classes, which cannot be what we want. So an option would be to use the training set, cut it into, for example, 4 pieces, and then apply 4-fold or k-fold cross-validation. And that's then just using a piece of the training set for evaluation all over again. And then we only use the test classes during test time, which maybe ensures us a bit more generalization also if we would apply our model to non-test set classes, but test set classes in the wild, let's call it like this. And there is a paper that brought this actually to the extreme, so to say. This is called Metric Learning Reality Check, where everything was fixed in their setting during training to ensure so what they say really, really fair evaluation. So even the batch size and even the learning rate and even like literally everything. And then they found that actually the, so to say, old approaches like contrastive loss or triplet loss did not perform too bad compared to new methods that were said to be state of the art. So you can see in the bottom of the slide that there are those more recent state of the art methods, like for example, soft triple loss. And in the very top of the table, you can see contrastive loss and triplet loss, which are from 2006, so quite old already. And according to like their study, we see that when we have a look at the right side of this slide, there's actually not really an improvement over the years and with this over the new works. While in the papers, actually, what we can see on the left side, a huge performance increase is always reported. But having a look at this, of course, we can now again ask ourselves the question, is this a fair evaluation protocol? And I might say maybe also not fair, because the question is, of course, does every method really require the same learning rate, the same weight decay, and the same batch size to perform best? Or is this maybe one step too extreme? And also, if we would go the other way around, should we just use old optimization techniques or old augmentation techniques just to ensure a fair evaluation, quote unquote fair evaluation, and stick with the so-called old stuff? And I would encourage you all optimally report the standard protocol and maybe also report the best way you can get, and always, really always mention what you do. I think that actually holds for every field and every paper, but mention which tricks you apply in the paper for sure. And take maybe current SOTA performance with a grain of salt, and keep in mind the things that we just learned in this talk, which maybe are not optimal currently. Last, what I want to give you is those two GitHub repositories where there are actually already nice code snippets for calculating the evaluation metrics that we introduced. So if you want to get started, then maybe check out those. This might help you in the beginning to get started. If there are now any questions, please let me know. Yeah, and thanks for your attention. Yes, sure. You can also come to the front and ask directly through the microphone, then I don't have to. Yeah, it can be.
So the Stanford online product seems like distinct from the other ones just because there seems to be diversity of classes. It's not so much like a fine-grained classification like from Does that affect performance at all, or is that something that you define with your approach that like it should be independent of the kinds of classes?
So the question was if, because Stanford online products, maybe we can go back a bit to it, seems to be, has more distinct classes than the other data sets, which is actually true, because in like CAS and CUP and InShop data set, we actually have classes that are more or less from one domain. So birds, cars, or images from online shopping. And the question was if, I forgot it again, if we take this into account, well, if that affects the performance. So if we have a look at the performance table, we have to say that it does not really affect the performance in this case. But I have to say also with Stanford online products that there are actually, is it five? It's five, right? Five meta classes, so to say. So bicycles, I forgot the others, but in total 5 meta classes. So it's actually also contains 5 smaller data sets of the same area, so to say. But I find it also pretty interesting that, for example, for CUP data set, the performance is worse than on Stanford online products, although we have a way wider variety of samples. But that might also be because sometimes those birds images, at least for me as a human, if I inspect them, for me, they are even hard to distinguish sometimes. So that is something that really, I think, affects the performance on CUP data set. So you cannot really say if it really affects the performance much because it's that different classes. But we will have a talk also on out of distribution, where you maybe get a bit more into like what happens if we have more out of distribution samples. Thank you. Yes. Yeah.
I've seen that it improved performance of the
That's cool.
Do you see any possibility in this?
So the question was, because we have those new works based on vision transformers, and they improve the performance on all data sets except InShop data sets, so except the fashion data set. And the question was if I have any intuition why this is, right? To be fair, I don't really have an intuition so far why this is. Does any of my co-tutorial organizers? Okay, so no, so far we don't have any intuition on this, sorry. But also the paper is super new, CVPR22. You can check out maybe the poster session and ask a question there. So yeah. Sorry about this. I think we can then go over to the next talk, which is Timo again. And thanks again for your attention.
Yeah, so thanks, Jenny. Yeah, while Jenny basically discussed very important issues with the current training evaluation protocols in DML, from a more, let's say, evaluation metric perspective, I would now like to discuss the current evaluation protocol in DML more from the perspective of the actual problem that we're trying to solve, which is an out-of-distribution generalization problem. But as Jenny already introduced, we're basically trying to transfer our features learned or our embedding learned on one set of classes to another set of classes, which is basically completely new and unseen, meaning we try to compensate for a certain shift in distribution. So just as a reminder, you've already seen this slide. This is the learning problem that we're facing, and we're trying to capture the similarity in our training distribution during training. However, in the training stage, we're actually trying to transfer our features to some unknown new feature distribution, which might be due to classes that are not part of the training set, unknown surrounding of our objects or even viewpoints, and also continual class changes. For example, if for vehicles, if the seasons are changing, and then the background is changing as well. So yeah, and when we talk about out of distribution, there's basically not really well-defined definition of what we actually consider out of distribution or how far is out of distribution, meaning while we can move from cars to, let's say, buses and thereby changing the form or like the shape of our vehicle, we could equally well also move from 4 to 2-wheel vehicles on the street, meaning we would have motorcycles which are even more distinct from cars, or we could even ask for really unbound transfer learning problems, meaning we made no assumptions or restrictions to our training test distribution, and thereby we could even ask to for example, to transfer and translate our model to birds, although trained on cars. And yeah, one can easily imagine there's basically an infinite number of different distributions that we could ask our model to transfer to. And then this basically means that to assess the real out of distribution generalization capability of our model, we evaluated on all of these kinds of distributions. So by aggregating, getting like a much better like intuition and statement about its actually generalization capabilities. However, in practice, this is infeasible. We cannot go for that. However, as it's currently done in deep metric learning, we go for the most naive and maybe most one of the worst solutions we can go for. We typically use, as in so many other fields, a single fixed train split, meaning we have our training classes. And like, for example, Jenny explained, we take the first half of our classes for training, the second half for testing, and this we then consider our learning problem. In Zoom? Stay tuned. Share the screens in tune. In Zoom.
But stay tuned.
But still stay tuned. Thanks. Yeah. So like I said, I mean, what we're basically doing is just some randomly splitting our classes into a train and test set, and they thereby consider fixing also the difficulty of our learning problem, because difficulty is actually dependent on how close are those two distributions, meaning how far is basically the jump from the train to the test set. Yeah. And even worse, which is something that Jenny already discussed, is that we're actually training with test class feedback, since we don't have some in-between validation set to tune our hyperparameters. So there's actually like quite some issues with the current evaluation protocol. And besides pointing out what these issues are, I would now also like to propose some solution to that, at least to the, let's say, approximation of the true problem that we're facing, which is basically out of distribution to an unknown, out of distribution generalization to an unknown train test distribution. So what do we need in order to construct such a, or to come up with a better evaluation protocol, maybe by extending of what we already have? We would ideally first be able to measure the difficulty from the train to the test set, meaning the difficulty of the learning problem. And ideally, being able to measure it, we can also change it and control the difficulty of the learning problems. Being able to do that, we could maybe, let's say, sample a set of learning problems, meaning train test split of different difficulty, and thereby ideally approximating somewhat the reality that we're facing. And to ensure, like, let's say, a better comparison to what has been done before, we would thereby ideally maybe consider the data sets that we have used so far, meaning cars, UB, or SOP, and thereby basically move within familiar realms. And I would now like to propose a solution, or like show a solution. That's the paper that we already published, which kind of takes these things into consideration and uses them to turn any benchmark set into, let's say, better defined or like a more realistic evaluation protocol for out of distribution generalization. And the method is basically so the first thing that we actually need to do is we need to be able to measure the shift in the different thread trainings and test distribution, meaning we need to be able to measure the distance between our distributions. And like measuring distances between distributions is not an easy thing. And if you want to do it exactly, but as we can, for example, have seen in the generative modeling community, there are some ways to do that. For example, the Fréchet inception distance, which is a popular measure to assess the quality of generations of, for example, GANs, EAEs, and so on. And the assumptions here is that we have some metric space that is typically represented as like some general metric space, which is able to equally well describe all the distributions that we like to compare with one another. And thereby we typically use some pre-trained image of representation, since those representations are very general in their features and have very few, let's say, biases towards certain kinds of features that you might get if you, And another thing that we assume in order to formulate the analytical to get a closed form expression of the free exception distance, we assume our data distributions to be approximately Gaussian in this metric space M, meaning that and this is also like an assumption that it has been done and has been made a lot of times in machine learning. And typically we find that this is, although it's just a very, very hard assumption, it kind of works well, at least for the problem of kind of letting approximately measure of how close the train and test distribution, or how close distributions in the metric space are. And the procedures that we can use in order to construct a set of different learning problems of different difficulty are actually quite simple. We basically propose iterative class swapping, iterative class removal. And I would now like to illustrate how these things work and how you can take or turn any benchmark set that you have that you like into a more or less assessment center for out of distribution generalization. So let's first start with iterative class swapping. Let's assume we have our default train test split given, which could, for example, be what we typically have in deep metric learning, meaning the first half of the classes are considered a train set and the second half is considered a test set. And what you now like to do, and what I have to do in order to make the learning problem even harder, is to identify classes from the test and train set whose exchange between the distributions would lead to an increase in difficulty, meaning an increase in the FID distance. And by exchanging these classes, we basically, again, arrive with a simple trick at a more difficult learning problem. And the same procedure we can actually apply multiple times up to saturation, and thereby actually creating a sequence of learning problems which are getting harder and harder, which we can basically include in our new evaluation protocol, which we can, for example, by averaging, get a more robust assessment of our learning problems, of our DML models. I'm sorry. The technicalities are not too important now. If you want to read about them, you can see on the paper. It's just you can simply calculate, for example, like a procedure to do that by only going for the means. You don't even have to go for the full approximation of the FID distance. And getting this, like applying this procedure up to saturation, meaning that we cannot find any more classes whose exchange will lead to an improvement or like increase in FID. We can basically also plot the difficulty of these learning problems over the iterations of class swapping. And here denoted as the blue curve, we actually see that the difficulty of our learning problems is monotonically increasing. And what you also see is that the data splits denoted in red that we include in our evaluation protocol are actually up to multiple times harder when it comes to this measured than the default splits that are typically used in DML. And the same progression are basically observed also in the other data sets. And just one additional hint or like highlight is that under SLP dataset, the default train test split denoted in the black dot on the right plot is actually very close to an in-distribution generalization problem, meaning that train and test distribution are very similar to each other. So the second procedure that we then applied after saturation to construct even harder learning problems to really extend our set to the maximum we can go for is the iterative class removal, meaning after saturation of our of the class swapping procedure, we can ask for those classes that are closest to the margin between the distributions. We can try to find them, and by removing them, basically we increase the margin between the two distributions, and thereby creating even harder learning problems. And again, this can be simply implemented and performed by simple class mean comparisons. So the details you can find in the paper, it's not too important, it's just that I would like to understand the concept. And again, if we visualize the difficulty of our learning problems, if compared to the hardest problem that we got out of the swapping procedure, we again are up to multiple times harder on top of that, meaning we're really like constructing a set of learning problems that are going from very, let's say, very easy, starting from the, let's say, default train test split to the realm of really hard problems where train and test classes, given the same benchmark set, are as far as possible from each other. And we can even also visualize this by means of TSV or UMAP visualizations. Here from left to right, we see examples of an easy, medium, and hard problem. And in the y-axis, you basically see the different data sets being plotted. And we can really see that with each going from easy to medium, from medium to hard, the overlap between train and test distribution is getting smaller and smaller, meaning that we're pulling the two distributions apart from each other, and thereby can verify that the increase in FID is actually corresponding to harder learning problems. Yeah, and having such an evaluation protocol, we then also applied it to the current landscape of DML models, where we basically, or very simply use one or two as representative of each of the categories of DML losses that we already introduced in the first talks, and just probe there basically how they progress and how they scale with the increase in difficulty by means of their recall performance. As well as you can see, like some observations is that intuitively all the methods basically perform worse on harder learning problems, meaning the harder learning problem, the lower the performance, which is intuitively clear, I think. However, we actually also see that different methods scale differently than others, meaning different methods are more robust than others. And this is really like a feature of this new evaluation protocol, that while on the default train test split, there was some kind of saturation setting in for performance. However, if go to for like harder learning problems, we can really highlight, let's say, differences between approaches and their performance and robustness better than only sticking to the single randomly fixed difficult learning problem. And one other observation that we made is, although proxy methods are typically very strong, given the special distribution of classes and samples in the SLP dataset, those methods seem to lag behind surprisingly in performance a bit compared to other strong methods, like, for example, methods from the ensemble DML category. We also use our triangulation protocol to probe the generic representations that are out there, for example, the CLIP model or the align model, which showed remarkably strong zero-shot classification performances. So we also wanted to ask ourselves, how strong are their models, or how robust are they actually on the DML benchmark sets? And we can actually see there's quite some differences between the data sets. On COB, for example, those strong models like CLIP or like vision transformers trained on huge training data, like up to 300 millions of images, they perform very well on COB. Which, however, might also be that maybe the train test distribution is already somewhat included in those training protocols. However, on other data sets like cars and SOP, we actually see that although these performance, given that they're not adapted to these data sets, are very strong, explicit adaptation is still required to go for maximum performance. And finally, we also try to propose a solution or like some way to some general way to robustify models in DML with respect to larger gaps between training and test distribution. And here we try to lend concepts from few-shot learning, meaning that if we make the assumption that we have few examples available for training from the distribution that you would like to transfer to, we can actually see that robustness of each method here is increasing. Here by mean showing of the average, and we actually also see that the larger the harder the learning problem, let's say the larger the gap between train test distribution, the more valuable those few examples get for learning. And yeah, this is basically the end of my take on all of this digitalization. I hope that I could inspire you to think a little bit more into the problem that you're actually facing, and I'd also highlight or mention that this approach is not really restricted to DML only. This is a very, let's say, common and general method, and to apply to all kinds of benchmark sets, whatever model you want to evaluate. If you want to have something which is which also probes the direction of out of distribution generalization, then yeah, just give it a try and construct your own out of distribution assessment center, so to say. Yeah, and now I'm stopped talking, and yeah, maybe you have some questions, so yeah, please.
Now, as a closing talk, we will show you some connections. Some might be obvious, some might be not so obvious. And I have to say that this is just a collection of connections, but there are many more. So, because actually there are many more, DML is everywhere. So this is just an overview of the things that I will shortly mention. And we'll start with face recognition. And face recognition was actually already mentioned by Timo earlier. And face recognition, to be fair, is actually kind of the same as deep metric learning, just applied to faces. So for example, we have here, like most images here are from the mega face challenge. I sneaked some others in, but in general, the goal is if you have a query face, you want to retrieve gallery faces that show the same person. And there are actually overview surveys also on this, like for example, this one here. And currently the accuracy on, for example, this mega face challenge is 99.1%. So if you ever want to use face recognition, maybe try out existing approaches first, because they are actually really good already. But just short recap again what Timo said. The most famous approaches in face recognition are sphere face, cos face, and arc face. And they all start with the softmax loss that you can see here also, and then bring it to some kind of angle-based margin losses, so that they first set the bias to 0, then normalize also, first reformulate the product between weights of classes and a given sample, and then normalize the weights to being length 1. And then sometimes also the X length is normalized to 1, and then in the end we have something that is only dependent on the angle anymore. And then we can sneak in different margins. So for example, a multiplicative margin in the angle space, or a additive margin in the angle space, or a subtractive margin in the cosine space. And all of this then helps to further pull apart our class embeddings. Another thing that is actually, again, the same as deep metric learning or face recognition is person re-identification. And there are actually two common data sets, market data set and COHK data set. There was another one, but this one was withdrawn by now, which is called Duke data set, which you might have heard of. And those person re-ID data sets are actually evaluated on rank K and MAP, and rank K is very similar or the same as recall at K. And you here again have a query image of a person or a pedestrian, and you want to retrieve this pedestrian from a gallery set of images. And in person re-ID actually mainly used loss functions are cross entropy, or in this case, so-called ID loss, which is the same, but it's applied on IDs, and triplet loss. But then other things are applied that distinguish the different approaches. So for example, what is very common is to split a given pedestrian into several horizontal parts, and then have a more fine-grained part-based distinguishing process between different pedestrians. Or you could use attention, but attention here is mainly applied within one image. So actually you have an image of a pedestrian and find the most important position, so to say, of the image. Or you can also use auxiliary information like viewpoints or attributes. Attributes on the right side are again some kind of attention. For example, you use some attention to define the gender or to define the dress or the hair and so on. Or a thing that I've also mentioned in the last talk, you can use some post-processing and training tricks. And for post-processing, for example, this re-ranking was mentioned that improves the performance quite a lot. But currently the performance on market 1501 dataset is also at 98.3 rank 1, so really, really good. And that's why this community is actually moving towards more cross dataset evaluation or domain adaptation, unsupervised person re-ID or occluded re-ID. A thing that actually uses person re-ID then, and with this also deep metric learning, is multiple object tracking. And in multiple object tracking, we have the case that we have pedestrians, for example, walking along, like over a place or something like this, and you have a video of this and want to track a pedestrian walking through that video. And then you have tracks from the past frame here in the left image and current frame detections in the right image. And you want to assign those current detections with previous frame. And you compute some pairwise cost matrix for this and then apply a bipartite matching, so a unique matching between tracks and detections. And in the most basic case, this is done based on bounding box position or position information. But if we actually miss a detection in one frame and then have the pedestrian being at a very other position in the next frame where it was detected, this bounding box position information might not be enough anymore to compute the cost matrix. So we also use appearance information, so person re-identification here. And what we could do is we could first compute like cosine and Euclidean distance based on embedding vectors that we get from some backbone CNN and the intersection over union, so the position distance, for example, add those two up and have a pairwise cost matrix in the end. But we have to say that in multi-object tracking, pretty often just simple ResNet50 trained models are used when, and also they are trained with triplet loss or cross entropy loss only often. So the field is not yet there to really use more complex, so to say, metric learning methods. Then another thing that was also shortly mentioned by Timo already is 0-1 or few-shot learning. And in few-shot learning, the task is actually n-way k-shot learning, which means k label examples from each of n classes that we've not seen during training. So we want to classify a disjoint batch of unlabeled examples into one of those n classes. And for this, we always have some support classes, or mostly have some support classes. And we could, for example, then compute some class representative vectors CK, and by averaging over feature vectors of the support samples, and then in the end, compute a similarity to a test sample X. So this should remind you very much of deep metric learning, where we again want to have a super small similarity, a super high similarity or small distance between this class representative CK and the embedding of a query sample or the test sample. And the same for zero-shot learning holds, where we could actually use even meta information if we don't have any class representative given, and then from this meta information compute our CK. Then another thing that you maybe all have heard of is contrastive learning. And contrastive learning we actually use for self-supervised learning. And self-supervised learning is used because we have an ever increasing amount of data, and labeling data is super expensive. So we try to use this unlabeled data that we have for example, pre-training. And what happens is that we define some pre-text tasks for trainings where we get labels for free. So for example, we could predict the rotation of an image, we could solve a jigsaw puzzle, or we could solve a super resolution model. Or we could do, for example, something that is also used in this pretty famous paper or known paper, where we first apply some augmentations on a given input image. And then we actually use these different augmentations and apply contrastive learning on them, which means that we embed those two augmentations and want to maximize the agreement between them. So have a very small distance in the embedding space. So applying the metric learning. And finally, the last thing that I want to mention here is geolocalization, where we, for example, have a query street view and a satellite image, and we take the query street view image with our own phone and want to locate us in some given world. And then we need to first generate a street view given the satellite images that we kind of can compare to our query street view. And to do this, we can use a retrieval loss again. So for example, cross entropy or triplet loss, to have our two images, so the query image and the transformed gallery image, to be very close if they show the same location, or pretty far away if they don't show the same location. And with this, I would want to finish this short excursion into other fields. And yeah, as I said, there are many more, like text to and image embeddings bringing to the same space. But if you have any question to any of those, or maybe also any others, I'm happy to answer them. Or should we directly go to the final? Yeah, I think we finally go to the, we directly go to our final discussion, panel discussions. So if you have any question to my talk or to any other talks that we had before, just feel free to ask them. And I thank you for your attention once again.
So, for example, at the end of that, you mentioned text. So, natural language processing. So within that, then, with metric learning, this should be able, there's opportunities then for this to handle not only images, but different modalities that could be in a high-dimensional space. So, do you see, what are your thoughts on this working for other modalities in high-dimensional space, high temporal sequences, long natural language processing type entries? Would these methods be pretty adaptable to a bunch of different modalities? Would there be a bunch of changes that may need to happen? What would your general thoughts be?
So in general, I would say if we talk about natural language processing, there are already those basic methods where we encode, for example, image captions into some embedding space and also compare them to images then, which is also happening with CLIP, for example. In general, I would say that, of course, there would have to be adaptations made, especially on the backbone and so on. but I wouldn't see any reason why this might not work, for example, also for comparing trajectories in tracking domain.
Yeah, I think it really boils down to, are you able to find the similarity by means of some labels or whatever? For example, in NLP, what makes two sentences similar and what makes them dissimilar? I mean, if you're able to define that, then you obviously are able to apply all these models. But I think in NLP, it's not that, I don't know, that easy to define really what makes two sentences similar, right? There are different ways of, again, also like in images, there are different concepts of similarity that you could go for. So when it boils down, can you define some supervision signal which reflects the notion of similarity you want to go for? But once you're able to do that, I don't see any modality, or like the ones that you typically work with, that that should not be able to, let's say, be optimized by DML.
Probably one extra consideration there. Images are a bit specific in the sense that they nicely match what we do with deep learning convolutional neural networks, meaning like the inductive biases that we have there by means of a convolutional filters nicely work together with images. In other modalities, that's not necessarily the case, and we've been talking about regularizations and them being important for generalization performance. That's where you might lose something. You would need to come up with different inductive biases that are appropriate in that case. On that same note, however, we've seen that transformers pretty much dissipated into the field of computer vision from natural language processing, and there, that being a one-dimensional problem, that was a very effective strategy. So what I said beforehand evidently does not exclude these models working in other modalities. It's just, it might be that you need to take a different angle. When it comes down to audio processing, people actually started the other way around, went for all the fancy features that existed there beforehand, and then learned that you can, to a certain extent, just apply your convolutional operators there as well and get better performance out. It depends, other than that, yeah.
Yes.
I just have a question. So really, it's in terms of the potential learning loss function proposed, and then yeah, also a bit of the gravity. You mentioned the learning gravity check paper, and but I think that paper also say the comparison in that paper is also kind of low that check there. And so my question is, how do you think, what's the correct way to compare the loss function in the current situation?
I'd say, while there are common factors, for example, like the dimensionality of the embedding space and so on, which increasement of that typically, works well for all the other. For every method, like trying to fix something like that would, I'd say, makes sense. But for example, fixing, I don't know, things like batch size and so on does not really make sense, because there are methods which are basically driven by larger batch sizes, meaning, for example, considering more, or like especially hinging on like the contextual DML losses, which basically are driven by lots of those relationships between samples. But yeah, you have a point there. The question is how to evaluate those methods like fairly. I'd say in the end, it's like more experience always helps. So try to maybe also use different setups. Maybe see yourself, okay, what is the current state of the method that you want to compare to? Try to maybe compare your method, or like train to your method in a similar setting. And if there are differences, discuss why there are differences. So it's the end, it's maybe not always about like always beating the others, but maybe also showing that you're more robust and so on. And yeah, in the end, also transparency is again a huge driver for fairness, I'd say. But yeah, nailing down every single parameter for comparison is probably not what we're gonna go for. At the same time, like, I don't know, like being wild west about whatever you do is also not really what you want to have. So it's, yeah, finding something in between is something that we have to settle for. And I think that there are lots of papers which more or less operate on a very standardized, let's say, setting, which kind of, driven by lots of papers. like seems to be like the essence of what works kind of well. I think the point of our talk was just there are sometimes some, let's say, black sheeps that are hiding their tricks and ramp up the performance in order to maybe for the sake of publishing. And this not only happens in our field, this only happens in other fields as well. It was just a reminder. Also, if you, for example, review those papers, always be like, you know, very suspicious about how the settings are comparable. But there is no such thing as the one best evaluation protocol which fits them all in terms of fairness and so on.
Yeah, I think most of the tricks, for example, the batch size, how to pre-processing the images, all these things can be fixed. But I'm just wondering more detail about the loss function. Since each loss function maybe has their own gradient to update the model. And I just think is there a fair platform, I would say, can help us to just comparing the gradient instead of comparing the other factors.
Yeah, I mean that might be an avenue towards the problem of introducing like as much fairness as possible into the field. So I agree with you. I mean, one would have to maybe try it out and come up with a solution to that. So yeah, I mean, if you want to work on that.
Yeah, we can discuss more later.
Yeah, sure.
So great tutorial, thank you. I just wanted to ask, because you brought up how just changing the background to sort of like the transformers or the hyperspectral transformers significantly increased performance. But recently there's been the Context paper which showed if you just do all the modern tricks with the convolutional neural network and the large scale pre-training, that you get similar improvements, and maybe that CNNs are even better for transfer learning, which is a current paper. How do you see that sort of affecting sort of that ranking that you presented in terms of like, hey, vision transformers are doing the best now? Do you think that is sort of re-ranked in context of?
Yeah, that's a very fair point, and I think that's popping up like a lot currently, where people say, hey, but if we kind of spice up ResNets or something like this, then we are at the same performance again. And to be fair, I think I haven't seen numbers on this so far, so that would be super interesting comparison for sure. And also, yeah, we've seen that the transformer performance actually also only like gives a really, really crazy performance improvement on one data set, on two a slight, and then one no at all. So yeah, it has also be taken with a grain of salt, but it would be a really interesting comparison if you would also show ResNext with this, for example.
Just to set that in perspective, I mean, other fields like visual synthesis, for instance, where transformers seem to rule for quite some time, there's also a transition to a certain part happening to diffusion models, for instance, or a combination of the two strategies, despite evidently knowing that the other methods that you mentioned also being there. It's still like the best methods there today, I would say, it's kind of fair to say, are diffusion-based methods there.
Thank you.
So I have a quick question related to the way we compute everything on a hypersphere. So I was wondering if the main assumption was, so we stay away from the stability of training. Do we lose anything by computing similarity on a hypersphere? Because I guess like in your trick slide, you're saying that beta normalization use those kind of similarity and so is there something that you use
yeah, actually that was exactly the point of this trick that was introduced in the paper with the beta normalization, that the authors said that you lose this length information that they found to be helpful also to some extent. But still, I don't know if that applies to every single paper and every single method. I feel like this like the final embedding vector also depends on the method, how you train it, and so on and so forth. So maybe that also depends on the method that you're actually training. And what you said, losing, of course, you're losing the length information. So if you say one class is defined by having a really short, so to say, embedding vector, while another one is defined by having a super long embedding vector or with a great length, then yeah, you're losing this information by scaling it to the hypersphere. But my intuition would be that this heavily depends on the method that you use. No worries.
All right, let me read a question from the chat. Can you please elaborate on the image augmentation few-shot example? What would be the negative example?
Yeah, in this contrasted learning, actually what you do is you have as a positive example those samples from the same image, and you consider actually each image as its distinct class in this case. And negative samples are actually samples from that you can generate from other images. So what would happen, you would, for example, sample, let's say 10 unlabeled images. For each, you would generate 2 augmentations, which give you 20 samples in total for one batch. And then just the images corresponding to the same image are the positive samples, and all other samples are the negative samples.
Thank you for this my question was related to the question of the other guy. In all the distance you are related to triplet this distance, you are considering between the features between the men, you are still considering that we are living in Euclidean space. But we don't know actually. We don't know that embeddings are really living in Euclidean space, in Riemannian space, or whatever space. So it's also a question to try to assess which is actually the right way to compare and this embedding. So any thoughts about this kind of problem? Because it was a little bit overlooked so far.
Yeah, I mean, so I think the constraint to the high unit hypersphere and going for Euclidean distances is something that just works very well in practice. There are also approaches, for example, based on hyperbolical embeddings, for example, which are obviously following different metrics there. And they also perform quite well on certain data sets and so on. But the difference is not too large, so to say. But you're absolutely right. I mean, going for one embedding, like, or one constraint on the embedding over the other, are there better embeddings, or like better constraints or better assumptions on the manifold where like the images are actually living? Can we find something better there? This is an open question, and so far I have never like really seen any work addressing these issues, and it's not that easy to I don't know, try to learn some prior on your manifold. But I agree that it would be something really exciting to see if this just works. It's just that lots of fields basically seem to agree on the constraint of the hypersphere. Like I said, contrastive learning, few-shot learning, metric learning. So I'd say this is more or less empirically driven, and due to its simplicity, so to say, and the familiarity of like Euclidean distances and so on. But there are also like other solutions, like for example hyperbolical embeddings, which also perform quite well.
Let me read another question from the chat. DML is usually used to identify objects of same identity, while high distance value between two images indicates are likely two semantically different objects. A low value does not necessarily indicate the same object. Like back views of two different persons may look similar, but from the front end being different identities. So is there any confidence measure to detect such ambiguous cases where a low metric value doesn't represent identical objects?
I'm reading these questions regarding like confidence of DML models, or maybe also outputting some kinds of variance of how sure the model is about its prediction and assessment. There's not too much work out there so far, but there's, for example, also like on the CVPR, there's a paper on that by Karsten, who's kind of investigated a bit in terms of proxy learning with confidence and so on, at least some probabilistic formulation at least. But yeah, like trying to somehow infer confidence in like try to get your model to tell you how confident it is about its prediction. There's not too much work about that. There is some work about maybe that's the recent year. I just don't recall it from the top of my mind, but there are, let's say, formulations which go more in the direction of like some, let's say, probabilistic modeling, where you may more or less say, okay, instead of trying to map a point to a fixed location in your embedding space, you formulate it by means of a distribution over its like potential location there, and then you, I don't know, there is a lot of different, let's say, family of optimization of loss functions that are opening up there. For example, divergent-based objective functions and so on. But this is a trend that just currently emerged, and yeah, we didn't cover it in the tutorial so far because we tried to go for basic concepts and what's been established as quite robust and performing well. But this is, let's say, one of the more recent trends of also like going for probabilistic models, which you typically also can use in order to also compute some confidence there, obviously.
Thanks for the nice overview. I do have a kind of a practical question. So what's the typical trick to do when you have a very high interclass variability? I know, for example, if you're trying to do a bird species retrieval, and then you take birds of paradise that can be crazy loops all around. So I read some kinds of easy positive sampling. I don't know how it works. I don't really work with the decent sampling strategy, or you have something else to recommend. So the idea is that you don't want to let nested collapse all.
Yeah, I mean, you have a fair point there that you know, there for some time the holy grail was collapsing your class like to as compact cluster as possible in your embedding space. But then there has been some works which kind of are going for the opposite in terms of regression purposes, because the more you collapse your class in the embedding space, the more invariances you learn, the less, let's say, tools your model has to describe new classes that has never been before. Yeah. So retaining information about intra-class variance obviously is beneficial there. One example, for example, is from the family of ensemble-based DML, where we tried to combine standard class discriminative learning with more complementary features, like features that are, you know, can be found in different classes as well. And this is more or less also like translating to also retaining features that describe the samples within a class, so to say. Yeah, because for example, if you retain color and so on, you will be able to unfold your car class into, you know, this is the car in different colors at least, and you can, yeah, extrapolate from there. So from my standpoint, I'd say it's important to at least observe how, if you train your model, how far is collapsing the classes, and if this is actually what you want. Yeah, like I said, thinking about out of distribution. If you're staying within your distribution, it's fine. Collapse your classes whatever you want. But if you want your model to be expressive and informative about unseen features, I suggest to at least thinking about like where you want to transfer to and how much of the features you want to retain, and then rather go give methods a try which try to compensate for the let's say collapsing effect of discriminative learning.
Also, apart from this, the method that Timo mentioned, for example, in soft triple loss, that was mentioned, I think, in Ismail's talk, there, for example, they also take several class centers per class to kind of account for this.
Let me read another question which just came in. Any thoughts on extending DML to more complex images with occlusion, or say multiple objects in the same image, where it becomes difficult to define positive and negative samples?
So I haven't seen this in deep metric learning, but I have seen this in person VID, where actually I mentioned this shortly, this occluded person VID. Currently, there were like, I think 2-3 papers in the last year on this. And in this occluded person VID, it was, for example, either a person being occluded by another person and then having to retrieve, like seeing this image as positive for both pedestrians, or the other was also if two persons were walking side by side and then you have a query image showing only one person and you also want to retrieve kind of the person, the image with the two persons on it. And if I remember correctly, images with two persons were then also considered as positive sample. But for example, attention was applied in these cases so that you really only attend on that part of the image where you see the same person as in the given query image. But for deep metric learning with objects or something like this, I've not heard of this yet.
All right, if there are any urgent last questions, then thanks everybody for being here, for chatting with us a little bit about deep metric learning. I hope you find this as exciting as a topic as we do and see all these applications. And I hope this has helped you a bit utilizing it here or there, or better utilizing it in the particular application that you're looking at. If you have any follow-up questions, feel free to just shoot us an email. As we said beforehand, on our website, there's the slides already uploaded, and we will also post the video eventually online there. And with that, thank you all for your attention, and happy to see you here around it in the conference and following days. Bye-bye.